Okay, June 15, 2023. Right now, we are almost done with chapter 16. Transverse wave. We did transverse wave with speed on a stretched string. What we didn't do was this one here. Energy and power of a wave traveling along the string, okay? We did the wave equation, interference of waves, phasors, and standing wave and resonance. Now let's cover a little bit of that as well. And then we're going to get into a new chapter. Don't forget, exam is Thursday next week. And by the way, today is Thursday as well, so 1 week from now. And here you go. Okay, so notes right in here. And one more student coming in. Okay, that's going to be 16.3. 16.3. I'm doing slightly different from the book. I think that my derivation is better, actually. Homework assignments due. The homework assignments are due. It's written there in the homework. Okay, I believe it's the last day of class or the following day of class. Let's take a look. Let's take a look. Here you go.
So all the assignments are due on the same day?
Yeah, that's right.
Okay, thank you.
So July 14th, 11:59. Okay, but you're better off to do the homework, to do the homework of the chapters that we have already covered, right? We're gonna finish this chapter here, 16. We finished 15. And I'm thinking about jump to 33 and then go back to 17. Okay, let's see how it goes. Okay. And energy and power of a traveling wave. Okay. So let's take a look at the string again. Here you go. We have the string oscillating back and forth. Okay. And this string has some mass. And if it has, because it's moving, it has some kinetic energy. But on the top of that, it also has some potential energy because it behaves like a harmonic oscillator. Each infinitesimal mass behaves like an harmonic oscillator, right? So, but let's take a look at the kinetic energy, the equation for the kinetic energy of an element of mass, dm, an element of the string dm. Okay, and this one here. Kinetic energy of an element of mass of a stretched string. Just remember that the position of the wave equation is something like that, right? The position of each element of the string is something like that. At given instant of time, some elements are a little bit further away from the position of equilibrium, others are closed, others are exactly at the position of the equilibrium. That's what this equation is telling us. And that's exactly what this illustration shows us, okay? I'll give it the instant of time, this element of mass is at this position, this other element at this position, and so on, right? And this element here, infinitesimal element. Oh, screen sharing. Thank you. Oh man, you gotta develop the habit of sharing the screen. Here you go. Thank you. Well, okay, here you go. That's an illustration in your book, right? At given instant of time, this element of the string is at this position, and that's exactly what that equation states. At a given instant of time, right? A little bit later on, the positions are going to be shifted a little bit, right, to the right. And that's what that equation is describing, the position of each element of mass. And each element of mass also has a kinetic energy. At this instant of time right now, this element of mass of the string has a kinetic energy that's equal to 0 because it's about to move in the other direction. This one too has an instantaneous kinetic energy that is equal to 0. Okay, then in this one here, this element of mass has a higher kinetic energy. Okay, and then so let's write down the kinetic energy of each element of mass, just like the book did. Here you go. The kinetic energy. Let's write that down like that. I'm gonna put in a proper order here. Here you go. It's going to be like that. Okay. The y component of the velocity squared. But the y component of the velocity squared is just the derivative of this equation right in here, okay? Of this equation here. So we already derived something like that before. Take the derivative of sine is a cosine, right? The derivative of sine is a cosine. Then you have to worry about the argument. The argument is going to have the derivative of this argument here is going to be minus kV, just like you have here. And that is the velocity of each element of the string. Going back to my kinetic energy, for the kinetic energy of a given element, we get this equation. dm is right in here, dm vy squared. Okay, you can derive that yourself, a straightforward calculation. Remember, this k is not the spring constant at all. Okay, recall that the k above is the angular wave number, right? The book called that angular wave number. Some books just call it wave number. Some other books just call it wave number. And then what's the next step? The next step is to rewrite your dm in terms of the linear mass density. Okay, dm dx is the linear mass density. Consequently, dm is mu times dx. So we plug that right in here. And that's what we did. Mu dx. Mu dx, I'm going to highlight it so you know, I'm going to highlight this one as well. Right, and highlight this one here so you know where it went. But this kV, remember, can be written in a different way. kV, a simpler way, we're just simplifying the equation instead of carrying several components, right? Of the several parameters, we carry just one. Those two parameters can be combined in a single one. K is 2 pi over lambda. V is lambda divided by period, which is also lambda times the frequency. And what we end up getting, the lambda cancel out with the lambda. What we end up getting is 2 pi f, which is, by the way, is the angular velocity, angular frequency, the angular frequency and angular frequency. And then we substitute right here, we get omega squared. Okay, I will put it right here in this other equation. So you have all the steps. Omega square goes right in here. And I don't need the mu dx anymore. Highlighted. I need only the omega square highlighted, right? Only the omega square highlighted. And then in the next step, look that we have a dx here, right? What we're going to do, we're now going to find the change in kinetic energy, the rate, find the rate of change of kinetic energy, okay? Which is going to be, all you have to do is to divide dk by dt, okay? And when we divide dk by dt, we get dx by dt right here. And this dx by dt is nothing but the velocity of the wave. Okay? That's what we get for dk dt, the rate of change of kinetic energy. I don't need my V highlighted anymore. Just recall that the total power has to be dk dt plus du dt, right? Kinetic energy plus potential energy. And now we're going to calculate. What the du dt is going to look like. The key piece of information, let's not describe it there in the book, is that each mass element of your string behaves just like an harmonic oscillator that oscillates back and forth here. This one too oscillates back and forth. This one oscillates back and forth. So it is as though each element here is connected to a spring, okay, with a massless spring, attached to a massless spring, oscillating back and forth, okay? Because of that, we can state that each element has a potential energy given by half. Now notice that I put a K prime here. I didn't put K, okay? What I'm using as lowercase k is the wave number, right? So instead of using the letter K for the spring constant, I'm using the K prime here, times y squared, the position square, which, by the way, is given by this equation here that you saw there. Now, there's a very important trick here. Very important trick. Recall from going back to the simple harmonic oscillator, right? We found that, I'll put another one here. We found that the frequency of oscillation was 2 pi, 1 divided by 2 pi, square root of that. But then we also had this other relation, right? The relation for the period, which was what? It's just the inverse. M over K prime. K prime. So what are we going to do here? Note that my string also has a frequency of oscillation, angular frequency of oscillation, right? So what can we do about that? We can, relate the K prime that is right here in our equation with the angular frequency of oscillation and the mass, the element of the spring, okay? Of the spring, of the string, the mass element of the string. If we do that, we can plug it in right in here and get the K prime in terms of the mass element of the string, okay? And I want to see that what we get here, K prime equal to omega square times M. And don't forget, this omega square is exactly the same one that we see right here in this equation for the kinetic energy. Because we're talking about an element of mass, dm, the K prime that is my potential energy turns into a dm omega square. And that's what I have here. I'm going to highlight it here. Here you go, K prime, both faced. But look at the difference between the potential energy and the kinetic energy. The potential energy has the position y squared, right? Whereas the kinetic energy doesn't have the position y squared, it has a velocity y squared. Velocity of the element square. Okay? There's the important difference between the kinetic energy and the potential energy. But let's continue here. And we're going to do exactly what we did before for the kinetic energy. We are going to rewrite the dm in terms of the linear mass density times dx. Okay? Since now we're talking about the element of mass dm, then we have to rewrite our u in terms of the infinitesimal potential energy of that element, du. When we substitute, we get something similar that we got for the kinetic energy, right? Mu dx. And then we do exactly the same thing. We get the rate of potential energy in that the string is using. We get the dx dt all over again, and finally the v. This is my final equation for the rate of potential energy. Okay, and I'm going to write it side by side. Here you go, here's my kinetic energy, and here is my potential energy. I'm going to write them side by side so you can see what happens. Mu v omega squared, right? Mu v omega squared, both have a half and both has a amplitude squared. It just happens that one has a sine square and the other one has a cosine square. Isn't that neat? They have exactly the same functional dependence. The only difference is that one has a sine square, the other has a cosine square. When we sum those two contributions, okay, we get the total power, the total instantaneous power of the wave. We don't even have to take the time average like the book did. Okay, you don't even have to do that. So du dt has a sign in there. Okay. And step by step, right? It's exactly the same multiplying factor. Sine square cosine square, that time dependence goes away. Which, by the way, that's the instantaneous power of your wave. The function of the linear mass density, the velocity of the wave, the angular frequency, and even more important, the amplitude of the wave. Notice that the power goes to the square of the amplitude of the wave. Okay? That's exactly what that woman in the TV series, PBS TV series said, right? If you double the amplitude of the wave, your power is quadrupled. Okay? So this one here was the step that the book didn't do. Okay? The book did the other steps. If you want, you can also get, if you want, right? If you want, you can also get the average potential and kinetic energies of the wave by integrating du and dk over time along for a single over time. Let's see, udt. Let's see. If you want, you can also get the average potential kinetic energy of the wave by integrating the u and dk, not over time, over the position in the wavelength interval. You can also do that. Okay. The instantaneous, just keep in mind that the instantaneous. So the first thing that you gotta do, no? You can also first get the, let's see, the instantaneous. First the instantaneous, right? Potential and kinetic energies of the wave by integrating du and dk over the position along in the wavelength interval. Then you take, then you can also the average kinetic and potential energies, okay, by, you can also obtain, right, the average kinetic and potential energies by integrating them along the, integrating them in time along the period of the wave. Okay. So just remember this, very important here. And let's take a look at the book, right? The book is that the rate of energy transmission, right? dk/dt. So the book did this, took the average. It's not necessary to do that to find the total power, as you saw. Okay. And he also mentioned that elastic potential energy is also carried along the wave and at the same average rate given by 16.3.5. He didn't prove that, okay? But that's the average. Okay? Although we shall not examine the proof, we should recall that in oscillations such as a pendulum or spring block system, the average kinetic energy and the average potential energy are equal. Okay, and then the average power, you know, it's not just the average power, it's also, oh gosh, what did I do? It's also the instantaneous power, right? Is 16.3 here. This equation that you see here is also the instantaneous power. Why you keep on doing that? 2, 3, here you go. Here you go. Mu v omega square ym square half. Exactly the same. Okay. So average, okay, the same equation, right? And by the way, very important, right? The factor mu and v in this equation depend on the material and tension of the string. That's understandable, right? The factors omega and ym depends on the process that generates the wave. The process should be the oscillator, right? The oscillator that moves up and down. The larger the amplitude of the oscillator, the larger the amplitude of the wave. The faster the oscillator, the higher is going to be the frequency, right? The dependence on the average power of a wave on the square, the very important, of this amplitude, and also on the square of its angular frequency is a general result true for waves of all types, not just the string. Okay, we didn't prove that, but that's the statement that he's making. I'm going to copy that and paste here. Okay, I'm going to. Although, here you go, I'm going to write it down. Although we derived the above equation for a wave traveling along a string, right? The above relation also applies to any wave, okay? But not the above relation, parts of the above relation, right? Parts of the above relation applies to any wave. And the part that we're talking about is this one here. And then I'm gonna put it here, string, okay? String, and then any wave is going to be proportional to that, okay? Not every wave is going to have a linear mass density, right? But it is true for those two terms here. It's true for those two terms here. That okay. And I'm going to erase this for now. Yeah, just this one here. And now we are done with chapter 16. Done with chapter 16. And we still did some of chapter 17 as well, because we talked about longitudinal waves. What I didn't tell you about longitudinal waves was what are the other ways of representing a longitudinal wave, right? So let's go back here. Let's see if I have an illustration for the longitudinal wave. No, it must be further down here. Okay, here you go. This one right in here. This is another representation of a longitudinal wave. Do you remember that I represented the longitudinal wave in terms of a transverse wave, right? But here's another way of representing a longitudinal wave. We can, we can come up with a representation of this longitudinal wave in terms of a transverse wave by drawing a sine wave that passes through here. Okay, the sine wave has its peak here at this position, has a node at those dashes, right? And then a valley at those positions. So that's a very good way of representing a longitudinal wave. Make sense? Compression, equilibrium position, and rarefactions. You're going to see this representation many times. Okay, it is as though as you have a sine wave there, right? Another way of representing a sine wave. And let's see what we cover on chapter. Any questions about that? Let's go there to the chapter 17. Speed of sound, traveling sound waves, interference, source beats. Okay. Let's see if they represented, they have the representation here, right? Okay, that's one type of representation of a sound wave. We're gonna get back to that. But before we do that. Oh, here you go. Here's the representation, right, of a transverse wave with the compressions and rarefactions, right, in a tube. Here you go, the compressions here and rarefactions. Anywhere, somewhere in between those positions, we have the air molecules that are in the equilibrium position, right? I had this representation also in my simulation. But if if you want to represent it in an easier way, instead of drawing all those dots here, right, which is lots of work, takes lots of time, all you gotta do is to draw a line, an interrupted line, a dashed line here, and just a single dash here. A single dash here. The distances between the peaks is the wavelengths. Okay. So we're not going to cover everything that is here in this chapter, but it's important. But before we do that, we're going to do something else. Okay. Intensity and sound level. So sources of musical sound. Okay. Here you go. Here are the particles, right? Oscillating back and forth. A representation of the particles oscillating back and forth. And that's the normal, that's the first harmonic. That would be the section on standing waves. Standing waves. Okay. Oh, here you go. So that was the section that we covered. So let's write that down, 17.5, right? We didn't cover beats yet, but we'll be doing that. We can even simulate this phenomenon here. We're going to be able to do that by using the resources in the internet. I always do that with my students when I teach this course. Doppler effect. Okay. And then we have supersonic speed shock waves. Okay, I will let you know which sections I'm going to cover, but right now we're going to do this one, and this one. We did this one. I don't think we'll be able to do that. Okay, interference. Maybe we can do that. This section on interference, but I will let you know. Okay, what I want to do now, I want to cover electromagnetic waves. That's how things are organized in my chapter, in my book, in my notes. And I even have to update the syllabus. Instead of doing chapter 37 right now, we are writing here. Don't forget, next Monday is going to be a holiday, right? So I'm going to put here chapters 16 and 33, E&M Waves. E&M Waves lecture. So we have to move this one a little bit down here, right? And 33, E&M Waves. And by the way, I got to save that as a version number 3. All right, then, and then we go back to chapter 17. Waves 2. Waves 2. Waves 2. And the exam, instead of 15 through 17, we're going to do 15, 16, 33, and sum of 16, okay? Sum of 16, which is 12 to 2 p.m., right? The last 2 hours of the meeting. And save that. Let's see, this one is going to be red to emphasize that we have an exam that day. 12 noon. XM, let's put here XM. 12 noon to 2 p.m. Noon to 2 p.m. Okay, so I think I have it the way I want. There is no bold space here. Let's see, any questions? Who has taken physics, electricity, and magnetism here? Who has done that before? Okay, anybody else? But let's take attendance, right? And then when I take attendance, then I will ask you if you have taken E&M yet. You have taken E&M, Chico. So Raymond did, right? Let's see if anybody else has done. And today is the 15th. Eugene Choi. I have a bunch of students that's not attending this week because they're having the final exam, right? And then you see system. I don't see Eugene here. Ashley Shu. I don't see Ashley Shu here. And Zakir. No, Zakir. Aini. No. Okay, Andy. Andy.
Hello, Professor.
Okay, did you take E&M, Emmy? Andy?
Yes, I've taken E&M.
You are taking or you took?
Oh, I took it before. Yeah.
You took before. Okay. Yes. Okay. Alex Hernandez. I'm not gonna punish you whether you or not. Okay. Hi, Alex. Are you there?
Yes.
You took E&M?
Yes, I did.
You did. Okay. Emily.
Hi, sorry, Professor. I might have to come back next summer instead of this summer. But yeah, I took the other physics.
Okay, the E&M, right? Okay, good. So what did you say about you have to come back this summer? I didn't quite understand that.
That I might do because I have class in the fall, so I might not take this class.
Oh, I see.
Right now. Yeah.
So you mean you may need to drop, is that right?
Yes.
Oh yeah, I'm sorry. Yeah. Too bad.
Thank you.
Okay, Sartak, Amerkar. Sartak. I don't see Sartak here. And Stephanie. Are you there, Stephanie? Okay, good. Did you take E&M, Stephanie? Yes. Okay, good. Who else? Zaid. You know, E&M is not a prerequisite for this course. You know, but so I have in the past I had students had taken only physics 37 and they took physics 39, even though they haven't taken it 38. But I think it's a good idea to take physics 38 before take physics 37. Physics 38 is the one that covers E&M. So Zaid, I don't see Zaid here. Next is Alisa. I don't see Alisa. Kartika.
I'm here, Professor.
Okay.
And I didn't take E&M.
The answer is yes?
I didn't.
Oh, you didn't? No, okay.
And also, I just wanted to let you know, I'm taking a class that has some overlap with this class. It's about to be done soon, but sometimes there's some timing overlap, and I've been trying to do both at the same time, so that's why I wasn't present for when we took attendance last time.
Okay. Okay, so are you a UC student?
Yeah, I'm a UC student.
Yeah, okay. Yeah, I have some
But I'm taking this class through another college entirely. But it's almost done, so I think after this week, I won't have that issue anymore.
Yeah, I heard that from other students as well. You know, they told me that this week is their final exam, week of final exam, and they couldn't attend the first week. Okay, thank you. Mary, are you there?
Yes, I'm here, Professor.
Did you take E&M?
Yes, I did.
Good, thank you. Raymond already said he took, right, Raymond?
Yeah, I also have a quick question about the notes for this class. So I accidentally bought the modern physics notes, which I think might be the wrong one. The one that has
yeah, that's right. There are two volumes, okay? The one that you bought is volume 5. The one that we are gonna cover that as well. We're gonna cover that as well. But what we're covering right now is volume 4. Okay.
Gotcha. Okay,
This
that's what I wanted to ask. Thank you.
Okay, welcome. Ashley Tai.
Also, Professor Sarthak is here.
Sarthak. Okay. You said, let's see. Didn't I put it? Yeah, I put here, right? Is that what you said?
Oh, sorry, Sarthak is here. He messaged in the comments.
Let me see here, Professor. I'm also here. Ah, Sarthak. Okay. Sarthak. Here you go. Thank you, Sarthak. And did you take E&M, Sarthak? Hello, Sartak. Yes, okay, good, thank you. Ashley, I don't see Ashley here in my list. Okay. Kyriakos? No, I don't see Kyriakos. Alexis?
Hello, Professor, and yes, I've taken E&M.
Okay, good, thank you. And well, I'm asking that because in order to do electromagnetic waves, we need the Maxwell's equations, and that's exactly what I'm going to do right now. Okay, Jeshwan, Mohan?
Hi, I'm here. I'm taking E&M.
Okay, the answer is yes, right? Okay, Basilio here. Yeah, Basilio is here.
Yes, I'm here.
Okay, do you take E&M, Basilio?
No, I only took in with mechanics.
Okay, only
37.
mechanics, right? You took E&M at the P7 level, right? At the algebra based level, maybe?
At the algebra level, yeah, but not the physics,
Yeah.
not the calculus level.
Yeah, not the calculus level. Okay. And then Daniela, I don't see Daniela here. We have 11 students. That's good. 848. Okay, let's take our break now before we start. Let's see what I'm gonna do. Now, let's cover E&M now. But one more thing, right? Exam 1, right? Chapters 15, 16, 17 point, let's see, 17 point. Yeah, 17.5. What about interference here? 17.5. Yeah, that's two. That's applicable as well. 17.3 and 17.5. 17.3, 17.5. Okay. And hopefully, yeah, we're gonna do 33 as well. Let's take a look at chapter 33. Okay. And this one is gonna go elsewhere. Let's see, let me reorganize it. Yeah, let's have our break now. Okay, so I'll break 8:50 a.m. to 9:05 a.m. Okay, and then we do, after the break, we do electromagnetic waves, okay? So
Hi,
yeah.
Professor Egalin. When is the last drop date for summer for this 5-week session?
That's a good question. Let me see. You're here. Let's see. There is. Let's take a look. I don't have it by heart, but it must be written here in the calendar. Here you go. Class schedule. Our session. Start here. Calendar. Summer resident registration deadline. Petition dropped with a refund without incurring. Check student portal for dates. They don't tell the dates, right? Drop a class without receiving it. Yeah. Check student. Did you find it? Drop a class as a W grade. Check student portal. Yeah. So I don't know. Okay. Use the class search on the college website or in the student portal to view add and drop deadline. Okay. I'm sorry, I cannot. I just don't know.
Thank you. I'll check again. Thank you very much, Professor.
Okay. Okay, so let's go for a break and I'll see you in 15 minutes. Okay, so we're back here. I'm going to start sharing the screen. And okay, in order to prove that that we have an electromagnetic wave, what we have to do, we have to start with Maxwell's equations that you learned in E&M. Okay, and going back here, let me see if this book did this book. Yeah, okay, they did something here. I'm gonna do something what I believe is better. Okay, and I'll do all the step-by-step derivation. And what are you going to do? I'm going to show to you that Maxwell's equations accommodates the wave equation as well. That's what I'm going to do. Right here, we go. It's possible. It is possible. Here, it's possible to prove that electromagnetic waves exist. It's possible to prove with Maxwell's equations, right? Maxwell's equations that electromagnetic waves exist. This was initially a hunch by Michael Faraday, but he could not prove. Mathematically. Math was not Faraday's strength. Instead, it took Maxwell. One of the reasons, no, there were two reasons why Faraday couldn't prove mathematically. One of the reasons was that math was not his strength, his strong point, was not his strength, right? Let's put this way, his strength. The other reason was that the equations of electricity, of E&M, all right, electricity and magnetism at his time was not completed yet. Instead, it took someone else to do that. And this person was James Clerk Maxwell. Clerk, right? James Clerk Maxwell. Someone else to prove that. James Clerk Maxwell. Okay, the way we do it at this level, in this course level, we use the integral equations. More advanced courses, we don't use the integral equation. We use the differential equations, the Maxwell differential equations. Okay, so we have all those 4 equations. Those are laws of physics. Okay, laws. Those are part of law. 4 of the laws of physics. Okay, here you go. This one is Gauss's law of electricity, Gauss's law of magnetism, Ampere's law, right? And this is Faraday's law. Sorry, this is Faraday's law. What you see here is Ampere's law, and then this term that you see here is the term discovered by Maxwell. So when Faraday was looking at those equations, he had only part of the puzzle. He had only this part here of the puzzle. After Maxwell managed to find this term here in this equation, this hidden term in this equation, he managed to prove that that electromagnetic waves existed. He managed to prove mathematically, right? Not experimentally. This proof was a mathematical proof. This proof was a mathematical proof, not an experimental one. Okay, It took someone else to prove experimentally that electromagnetic waves exist. Okay. It took someone else with a different set of skills, right, to prove that the electromagnetic waves existed. This person was called Heinrich Hertz. It's a fascinating story how he managed to discover, how he managed to prove the existence of electromagnetic waves through a series of very detailed experiments. But unfortunately, Hertz did not think that his experiments had any practical applications. Typical professor, okay? Typical university professor. They are just looking to show something, but not implement it in a practical manner, okay? It took someone else instead. It took someone else to reduce Hertz's experiments to practice. One of those guys won the Nobel Prize because of that. Okay, actually it took 2 people, right? At least 2 people, 2 researchers to reduce Hertz experiments to practice. One of them, you already know him. You have heard of him, Nikola Tesla. He made very important contributions to this field. But the other one that we remember the most for these contributions was not Nikola Tesla. You know, it was Marconi, Guilherme Marconi, an Italian researcher. Okay. I believe it's Marconi with E, right? You can check the history behind that. It's a really fascinating story, okay? The history of electromagnetic waves. Electromagnetic waves. Let's see what Wikipedia has on that, right? Electromagnetic waves. Then I always like to, no, not Hindi, no. In English. Wikipedia. Let's see what they have here. Physics theory, the history and discovery, right in here. History of discovery. Electromagnetic waves. Electromagnetic radiation of wavelengths of other than those of visible light. We discovered in early 19th century. 19th century was 1800s. You know, the discovery of infrared radiation, which is invisible to the human eyes, is ascribed to astronomer William Herschel. Okay? But at that time, they still didn't know it was made of electric and magnetic fields. Okay? They haven't proved that yet. But before it was proven, right? That light and infrared radiation are made of electric and magnetic fields. People already start to think whether there was any type of invisible light. And Herschel was the one who discovered infrared radiation, just by doing some interesting experiments, okay? And this other guy discovered ultraviolet radiation in an experiment similar to Herschel's. So what Herschel did, he broke down the white light from the sun with a prism, okay, just doing the rainbow colors, right, that everybody's familiar with. And then Herschel asked whether, you know, and then he started, well, wait a minute, he started measuring the temperature of each of those colors in the rainbow beam that he projected in a screen. Okay, that's what he did. So what he discovered? He discovered that outside this range of the rainbow, in this region here where everything was black, right? He discovered that there was some temperature in there. warmer temperature, warmer than the outside than the environment temperature. So what was his conclusion when he discovered that there was some energy here in this invisible part of the spectrum? He assumed that there was something called infrared light. Infrared means below the red wavelength. And then this other guy did the same thing. He made measurements in the other part of the spectrum. Here you go. In the past the blue. That's why it's called the past the violet color. That's why he called it ultraviolet. He discovered a rise in temperature in this region. Okay, but they still couldn't prove that electromagnetic waves existed. However, in James Clerk, right? Clerk, let me correct that. It's not Clark, it's Clerk. Maxwell. So in the mid 1800s, he developed equations for the electromagnetic field, which suggests that waves in the field would travel at speed very close to the speed of light. Okay, but he was experimental type of guy. He was not. He was a theoretical type of guy. He was not experimental one. The experimental scientist that came up and proved the existence of electromagnetic waves was Heinrich Hertz. Okay, and that was by using electrical circuits, not just equations. Right here in Maxwell, he used his equations to predict the existence of this type of waves. And Hertz, he was a university professor. He was not interested in practical applications. He was just interested in playing with toys, right? Advanced toys. And let's see, Marconi here. They don't say anything about Marconi, unfortunately. Yeah, okay, they don't cover the contributions of Marconi here. But so let's go here, Marconi. Guilherme now, Guglielmo is the name in Italian. In Portuguese and Spanish should be Guilherme. In English should be William Marconi. You go, that was the guy that made the proof not that proof, but he reduced Hertz experiments to practice. He was the inventor of the radio. Here you go, inventor of the radio. This guy used the inventions of Tesla to transmit radio signals at long distance in a wireless fashion. Okay, but he was able to do that only because of Tesla himself. Tesla was really disheartened that Marconi ended up winning the Nobel Prize with Tesla's invention himself. And there was a big fight between the two of them. And unfortunately, Marconi won, but then after Tesla died, everybody started to acknowledge that Marconi couldn't have invented the radio without Tesla's invention. Okay, and here you go, he won the Nobel Prize in Physics for transmitting, invention of the radio, inventor of the radio. Huh? But inventor of the radio means wireless radio, right? Because before Marconi, we were still able to communicate using wires, copper wires. Early years, radio work, from use. Marconi was interested in science and electricity. He began working on the idea of wireless telegraphy. They wouldn't call it radio, they would call it telegraph. The telegraph at the time needed wires to transmit the information, to transmit messages. Okay, so they would deploy kilometers and kilometers of wires just to talk among each other. What if they could that without any wires? So they could communicate to remote locations, right? That was the advantage of wireless telegraphy. And Go developing radio telegraphy. He used a monopole antenna. Induction coil, which was an invention of Tesla himself. And he sent his messages in Morse code, which is the simplest type of code that you're going to have, just dots and dashes that represent zeros and one, right? Think about that. The dots and dashes of Morse code is nothing but zeros, and this one should be a one too if you put it upside down, if you rotate it. 0, 1, that's the binary language. Okay, so let's go to the derivation, right? And the equations that we need to prove the existence of electromagnetic waves are those 4 equations here. 1, 2, 3, and 4. Okay, and there is a small correction that we have to do, a small, change that we have to do to those equations. And I have to illustrate that for you. And in order to prove that electromagnetic waves exist, we have to start with some type of device. Okay? The device that I am illustrating here is the magnetic dipole antenna. You have seen in electricity and magnetism that a magnetic dipole antenna is nothing but a circuit, a closed circuit, can be a circular circuit, can be a coil as well, in which you pass a current that changes in time, in which you pass a current, an AC current, that you change it in time. So I give an instant of time, the current is flowing in the clockwise direction, later on is flowing in the counterclockwise direction. You need to connect this circuit here to an AC source, right, to a generator. That's how electromagnetic waves exist, right? That's how you create electromagnetic waves, by using a current that changes as time goes by. And how do we do that? We go so far away from this transmitting circuits, from this transmitting antenna. An antenna is nothing but nothing more than a circuit. Okay, and again, I'm illustrating a magnetic dipole antenna, and you can repeat the same thing for an electric dipole antenna, which is different from that. Far away from this antenna, remember, we're trying to send signals in a wireless fashion, right? In this region here of space, there is no electric charges and there are no currents whatsoever. And that is the modification that we gotta do to Maxwell's equation, okay? Somewhere around here in space, there are no currents and no electric charges. So what we're going to do, we're going to make this term equal to 0 and this other term equal to 0 as well, okay? So now that's what we have, 0 and 0, and then we have just those 2 equations that relates the electric field to a changing magnetic flux and the magnetic field to a changing electric flux. There is some symmetry here. You see that? The integral is the same, it's a line integral. And on the left side is a line integral. And on the right side is a change in the flux of a field. If you have an electric field here, you're going to have a magnetic field here. If you have a magnetic field here, you have an electric field here. In this derivation, we don't need to use that anymore because we have just zeros on the other side. Okay? So we're going to concentrate on those 2 equations to prove the existence of electromagnetic waves. Here you go. This negative sign, as you recall, is Lenz's law, right? Changing magnetic flux induces an electric field, and then Maxwell discovered that a change in electric flux induces a magnetic field as well. But will these electric and magnetic fields, are they going to behave like a wave, like an electromagnetic wave, like an electric wave, like a magnetic wave? That was the question that scientists were making at that time, were posing to themselves at that time, okay? So let's start with this equation here. Going back to my drawing, right? We do know that this current is generating a magnetic field outside the circuit. Using the right-hand rule, we can state that there will be magnetic fields here in this region that will decay in time, that will decay as we go further and further away in space. Okay? So here you go. Here's the magnetic fields pointing in the proper direction, pointing away from the plane of my screen, right? That if we had a static field, a static current. But in reality, we do not have a static current. In reality, we have a current that changes as time goes by. Okay? That's what this current loop generates, a field. Okay? Don't forget that, just like I mentioned, right? This current changes in time. And if the current changes in time, the magnetic field is also going to change in time. There will be not only a change in the position of the magnetic field, just like you saw in the previous slide, but there is also a change, a temporal change in the magnetic field as well. Once you have a change in magnetic field, you're going to have a change in magnetic flux. Once you have a change in magnetic flux, you are going to induce a electric field, okay? Let's assume that this current is increasing in time, the IDT. We have to make this assumption to have a better idea what electric field that this magnetic field is going to induce, okay? If the current increases in time, the magnetic field is also going to increase in time. I can write down everything that for you, right? So let's do that before it becomes too much information, right? And in the process, we repeat, right? Let's see. So we start with a magnetic dipole carrying a current. Okay. Far away from the magnetic dipole, let's see here. Okay. So this thing here should be right here. Okay. We start with a magnetic dipole carrying a current. Far away from this magnetic dipole, there will be a magnetic field, right? I'm just repeating what I said there in the slides. But far away from this magnetic dipole, not only there will be a magnetic field, but there will be no currents or charges, right? Consequently, the right side of this equation is going to be 0, and this term here is also going to disappear. Okay. Consequently, the above equations, right, reduce to and I don't need that phrase anymore. Okay. So if the current is constant and does not change in time, right? The B field will also be constant, and the term on the right side of the third equation will be 0. Okay? Will be 0, and there will be no induced electric field, right? However, if the current changes in time, if the current changes as time goes by, then there will be a changing magnetic field, and a changing magnetic flux. The right side of the third equation will not be 0, and this changing magnetic flux will induce an electric field. Again, according to the third equation. Right? It is possible, as you know, it's possible to vary the current in my magnetic dipole by connecting it to a generator, which was a device that we explained also in Physics 38, okay? So going back here to here's my magnetic field now that's changing in time. This magnetic field is producing a changing flux in time, and this changing flux will induce an electric field that will circulate around the magnetic field lines. Can you picture that? Okay. This circulation is gonna point against the change in magnetic field. Because the magnetic field is increasing, I state that the magnetic field is increasing, then the circulation of the electric field is going to be against the direction of the magnetic field, okay? So each of those magnetic field lines will induce an electric field. That's what you see here is an electric field. I didn't label them, but it's an electric field. By the way, this is a semi-quantitative procedure, okay, which works very well. I cannot tell you specifically what's going to be the electric field that's circulating around here, the mathematical expression for the electric field, but I do know in a qualitative fashion that there is a circulation of the electric field around this magnetic field lines, okay? So what else? If you look closely at those electric fields that are here, right, and here, you can see that they tend to cancel out. The magnetic field line is inducing, this magnetic field line here is inducing an electric field to the left. But this magnetic field line here is inducing a electric field to the right. So what does it mean? It means that the electric field of this magnetic field line is going to cancel out the electric field of this other magnetic field line. Okay? Because the intensity of those magnetic field lines are almost the same. Okay? So I can say that there will be no electric field in between those magnetic field lines. The magnetic field lines in the vertical direction. This applies to this magnetic field lines, to this magnetic field line, and to this magnetic field lines. So just from this pictorial analysis, we conclude that there will be only induced electric fields in the vertical direction, right? Not in the horizontal direction. The one here on the right is going to be upwards, on the left is going to be upwards, the other one is going to be downwards, and then there will be an electric field associated with this weaker magnetic field. Okay, those two lines have the same intensity because they belong to the same magnetic field, but they point in opposite directions. Similarly, those two lines have the same intensity. That's why I drew them with the same lengths, and so on. Okay. But wait a minute. If this magnetic electric field is pointing downwards and this other is pointing upwards, there will be, there'll be a little bit of canceling here. Okay, there'll be a little bit of canceling out here. And that's what's happening here, right? Don't forget, I have more magnetic field lines here to the left, right? So this line will also be canceled out by the other electric field line that's going to come here. Okay, so overall, we are going to have an electric field distribution that's going to look like that. Electric field lines that point downwards. Okay, and the electric field lines are going to decrease as well because they're being induced by a weaker magnetic field. That's the picture that you have to have in your mind, okay? And then we go the next step. We recognize that there is a change in the intensity of the electric field. Okay, there is one, let's see, someone here, will the direction change if the direction of the field? Oh, yeah, well, wait a minute. You gotta be careful, right? You gotta be careful. The direction depends not only on the direction of the electric field will depend not only on the direction of the magnetic field, but it also depends on how the magnetic field is changing, right? So you may have a change in the direction of the electric field if the magnetic field changes, but you also have to look for this derivative of the magnetic field. Make sense? Okay. For instance, if this sign were to be negative, then the induced electric field would be in the other direction, right? So it depends on two factors. Depends on the direction of the magnetic field and depends on how the derivative of the magnetic field is changing. Make sense, Raymond? Okay. So to answer your question, if the direction of the magnetic field changes and this thing doesn't change, then the electric field will change. The direction of the electric field change, okay? But you have to look at those two factors, right? The direction of the field and how the magnetic field is changing. Okay, so let's see if it's possible to vary the current in my magnetic dipole by connecting it to a generator, right? So let's document what we have here now. Now that we have a changing current, right? That changes in time. The associated B field will, let's see, will also change in time. This changing magnetic field induces an electric field. Induces an electric field. This E field, whereas this E field circulates around the B field lines. Now, the direction of circulation, right? The direction of circulation depends on the BDT, right? Depends on the BDT. If the BDT is positive, if the BDT is positive, comma, the field will circulate in a direction contrary to the B field, right? If the BDT is negative, right, the field will circulate in the same direction, in the same direction of the B field. We have to rewrite it here, right? Let's rewrite. Here you go. 1, if the BDT is positive, right? And that's according to the right-hand rule. The field will circulate in a direction contrary to the B field, according to the right-hand rule. Okay. If the BDT is negative, the field will circulate in the same direction, of the B field according to the right-hand rule. Okay. Here's what I'm doing here is the script, right? The script of those illustrations that you saw. Okay. If fields between B field lines of same intensity, cancel out. Okay, cancel out to 0. Cancel out to 0, resulting in E fields that point along the vertical direction only. Okay, just like you saw here in the drawing. And what else am I forgetting here? Let's see. Is it possible to now that we have a coordinate change in time, the association B field will also change in time. Oh, there is one more thing here that I gotta put here, right? As we move, right? There's one more thing I have to put. As we move further away from the magnetic dipole, right? Magnetic dipole, the intensity of the B field also decreases. Okay? There'll be no induced electric field. However, also, and okay, this one belongs here, okay? Also, okay? That's what this term belongs here. Also, as we move further away from the magnetic dipole, the intensity of the field decreases. Okay, that's the important piece of information. However, if the current changes as time goes by, then there will be a changing magnetic field, a changing magnetic flux. The right side of the third equation will not be zero, and this changing magnetic flux will induce an electric current according to the third equation, okay? If fields between the field lines of same intensity cancel out to zero. Direction only, according to the drawing, right? It's called direction according to the drawing, to the illustration. So horizontal fields, horizontal electric field cancel out, only vertical electric fields remain. Okay? Because the B field decreases further and further away from the dipole, right? The induced E field can also be drawn as decreasing further and further away. And that's what we have here in this illustration. We finally get to the point where we are going to use the equations. We finally get to the point where we are going to be more quantitative in our derivation here. Here we have an electric field at position x at instant of time t. Here we have an electric field at position x plus delta x at an instant time t, right? So what we're gonna have, okay, we're going to start using those equations here. We're going to use the left-hand side of this equation, okay? Don't forget that this thing here is a path integral. That's why I drew, let's see here. Okay, that's why I drew this path here in this drawing. I'm making my drawing simpler, right? The less information we have here, the easier it becomes for you folks to understand what's going on, right? You'll see that in this case, I put my electric field at position x right here, and my electric field at position x plus delta x in the other one, right? I put it down. It's better if you make it closer. Even better, we put it here. And then, right, I already put my integral there to guide me, right? Here you go. And then I'm gonna draw my path. Can I put it here? No, leave it down there. There was a reason why I put it down here, right? In the first place. It's a little bit shifted, so this black doesn't erase my electric field lines. This black dashes doesn't erase my red arrows. Okay, so this integral is going to be along this path, okay, folks? It's going to be along this path. That's what this closed path integral is all about. So let's go. We gotta choose a direction of the loop. I have chosen a direction of the loop that coincides the direction of the magnetic field according to the right-hand rule. You can choose the other way too. Okay, but let's do this way. And you're gonna get the same result if you choose the other way, okay? Right-hand rule, my path, the path of the integral is following the direction of the magnetic field. Okay, and then we're going to have 4 paths, arm 1, 2, 3, and 4, right? That's when we break down this integral into 4 integrals along paths 1, 2, 3, and 4. We have more, let's say, don't forget that this rectangle has a side delta x, okay? And a length that we still do not know, L. I'll call it L. You're going to see later on that this L is going to disappear. You don't have to know L. And the delta x you're going to use for something else. You're going to see it, right? Also, don't forget that this path is in the direction, rotates in the direction of the magnetic field. Do you need anything else? Okay, let's see. Here's the electric field lines, right? 1, 2, 3, 4. The electric field line here on the left follow the direction of the path integral, and this other electric field line is contrary to the path, to the direction of the path of the integral. Okay, so going back to my calculations now. Do you picture what we're doing here? Right, many of those things we're repeating, right? So here you go. That's where the calculation, the series calculation come by. The closed path integral can be broken down as an integral along path number 1, an integral along path number 2, an integral along path number 3, I put 3 here, and an integral along path number 4. Okay? Along path number 1, it's not going to be 0. It's going to be different of 0. Along path number 3, it's not going to be 0, but it's going to have a negative sign here, right? Because the path is going to be is contrary to the direction of the electric field. Path is going upwards here, but the electric field is downwards. Along path 2 and 4, it's going to be 0 because there is no electric field in the horizontal direction. Okay, don't forget, it's a dot product. Okay, it's a dot product. E is those fields here. The field here is going to be in the vertical direction. There is no component in the horizontal. So when we break down my integral in 4 paths, the integral along this path and this path is going to be 0. Okay? Simple enough? Going back, that's why I have integral over paths 2 and 4 equal to 0. This dot product ends up being 0, right? It's not the integral that ends up being 0, but it's the dot product itself. Since the dot product is 0, the integral of 0 is going to be 0. Okay. And now we are ready to work on the other 2 integrals. 954. Okay. Now, since we have chosen a path along which the electric field doesn't change, we can take out the electric field term from inside the integral. Okay, remember, we're following this path along the integral. We're not following this path along the integral. If we're following the path along this integral, then the electric field would be changing, would be changing, and you couldn't take you wouldn't be able to take the E out of the integral. But because we are following a path along which the electric field doesn't change, we can take the electric field component from inside the integral. The same thing applies here. And that's what I did. Okay. See that? We have Ex of t along path 1, E of x plus delta xt along path 3. And I'm taking those E fields out from here and from here. And then finally, we have the path along the S. Okay. And the length of the path is L, and I put L here. Okay, so here you go. That's what happens to our integral that you saw. Okay, left side. And now we are ready to do this integral here. Okay, now going back to the drawing. The path is in the counterclockwise direction. What we have here is a path that encloses an area, right? This magnetic field is changing as time goes by. Okay, but because those magnetic fields are almost the same distance from the dipole, we can say that those magnetic fields do not vary along the x direction. Consequently, we can take the B field from inside this integral. Don't forget, this integral here is along dx and dy, right? That's what dA stands for, dx dy. Also, the dot product between B and A is going to be 1. It's going to be BD1, BDA. Why is that? Because both the area and the magnetic field, they point in the same direction. And when I mean the area, is the area of this enclosed by this path, okay? So we have this vector area here pointing the same direction as the magnetic field is pointing. That's why this dot product becomes BDA. And the magnetic field doesn't vary much within that area. Why is that? Because I'm getting a very small delta x, okay? And that's why I can take out the magnetic field from inside the integral. There is one more step here that I didn't do, right? Let's do it like that. I'm gonna make this step here. Okay, I'm gonna put it between parentheses. Okay, B x of t can be taken out of the integral because the delta x is very small. And the magnetic field doesn't change much within that delta x. The area doesn't change in time. For this reason, we end up just with a derivative of B with respect to t, okay? But wait a minute. There's more to it. It's not a total derivative. It cannot be a total derivative because the B is a function both of x and t, right? The correct way of writing down this derivative would be to write down in terms of a partial derivative. And that's what I'm doing here. That's what I'm correcting here. This area that you see here is going to be L times delta x. Okay? And what happens to the L that we do not know? They cancel out. Those two L's cancel out. We frequently see something like that in math and physics. Sometimes, it's a kind of a long derivation, right? But I hope you're enjoying it. Okay, and now here you go. What we have a delta x here on the right side, and we have a delta E on the left side. Everything is coming together. You see here? We pass the delta E to the delta x to the other side, and then what happens? We have a term here, the delta E over delta x. This delta E over delta x, take the limit as delta x goes to 0, it becomes dE dx. And now we get this equation here for this relation for the partial derivative of E with respect to x and the partial derivative of B with respect to t. Okay? And then we repeat, remember, it's 4 equations, right? I'm going to just remind you. We start with 4 equations. These 4 equations became only 2 because the first 2, it's just a zero identity. We don't need them. We use this equation here to find a partial derivative equation. And now we're going to repeat the same thing for this equation here. Okay? They are almost the same. The only difference is that we switch the electric and magnetic fields, and we do not have a negative like here in this one, and we have this constant that the other one doesn't have. That's the only difference. And then we gotta do the same thing. Okay, we do the same thing, but now we do it in a different direction. Let's see if I have the illustration here for the different direction. We have to rotate our space so we can see the electric field in a different direction. Either way, we're going to get a partial derivative as well. That is slightly different from the other one. Okay. I'm not going to do this step by step because it's going to take too much time, but the step by step is similar. The only difference is that you have to rotate, you have to rotate this drawing here with the E field pointing towards you and the magnetic field showing as lines going upwards, just like the electric field are showing lines downwards, okay? When you do that, okay, when you repeat for the other one, for this one here, you get this equation. And now we have two equations. This equation here and this equation here. The question is, do you have a wave equation there? That's the question that you got to ask yourself. The question is, does this system of equations reduce to the wave equation? That's the question that you have to ask, okay? And that's the question, and that's what Maxwell was doing at his time, right? But he was not doing with those 4 equations only. Maxwell didn't, the Maxwell's equation didn't come up to this point, hadn't already evolved sufficient to come to this point that we see with 4 equations. At the time of Maxwell, he actually had 30 equations, okay? He didn't have 4, 30 integral equations. But he still could see that those equations allowed for a wave, for the wave equation. How are we going to prove that? There is a very simple way of doing that. Okay, there's a very simple way of doing that. And what we have to do, here's the wave equation, right? What we have to do, we have to differentiate this term here, this equation here, with respect to x, partial derivative, and repeat the same for the other, okay? So here you go. I'm going to start differentiating either this one or this one, okay? Either way, you're going to get the same result. What I decide to do here, these notes, is to differentiate this equation by x. Okay, and yeah, we do get a second order derivative, but wait a minute. We didn't get a second order derivative. We do get a second order derivative here. We get a second order derivative in x, but not a second order derivative in time, right? But there is a way to reduce that to a second order derivative in time. How do we do that? All we have to do is to commute those two partial derivatives. What was dB dt becomes dB dx. What was ddx becomes ddt. Okay? And then what else do we do? We feed what we have here. Okay? dB dx is here. We also have dB dx here. This term that you have here goes inside the parentheses. And then, bingo, we have a second order derivative in time. The minus sign cancels out with the minus sign. And look here. Compare those two, right? The amplitude that you see here is a generic amplitude. It's not just the amplitude of your string with respect to the equilibrium position. It can be anything. Okay, this y that you see here can be also that. and can also be an electric field, can be a magnetic field. And look what we have here. Here we do not have 1 divided by v squared. We have mu naught epsilon naught. And what does it mean? It means that this guy here has units of inverse of meter second square. If you go ahead and do the calculations, you're going to find out that 1 divided by mu naught epsilon naught is going to be close to 300,000 kilometers per second. Okay? We repeat the same for the magnetic field, and we get exactly the same solution. Okay, and here you go. That's what we have. They both obey the wave equation. Not only they both obey the wave equation, but we have seen that they are perpendicular to each other. B field in this direction, electric field in this direction. Okay. But this perpendicularity, okay, occurs only in the vacuum. Other materials or other types of media, they may not be necessarily perpendicular to each other. That is, so Maxwell, you know, when he did that, he got this term here. He found out it was 300,000 kilometers per second. And then he starts thinking, hey, wait a minute. This speed is equal to the speed of the light. So it means that the other types of invisible light, infrared, ultraviolet, like they already knew at that time, should be propagated 300,000 kilometers per second, as well as those radio waves that Hertz discovered, right? And then later on, people discover X-rays, gamma rays, which are also electromagnetic radiation. That article on Wikipedia, right, mentioned that the discovery of X-rays, history, history. See, William Röntgen, right, discovered X-rays, and let's see, someone is coming. It was 1895. Okay, and microwaves, Hertz was discovered. Radio waves and microwave was discovered by Hertz, and gamma rays. Okay, gamma rays was the name given by Rutherford, but was discovered by Paul Villard. Gamma rays was discovered by Paul Villard. Okay. Wow, that's a long derivation, right? And let's, all right, already took attendance. What time is that? 10:08. Last time let's have our break right now. Okay, now that we know that the electric and magnetic field obeys the wave equation, we do know that they also can be written down in terms of a propagating wave, with the important difference that the v here would be the velocity of the light in vacuum, right? In vacuum. And there they can be plane waves. Okay, the K inside the planar wave depends on the frequency of the magnetic dipole. Remember, when we go back here, I told you that waves are a result of an oscillation. Here we have an oscillating current. So this oscillating current is creating a wave. Okay, it's not your material type of pendulum that oscillates back and forth. It's not your material type of spring that oscillates back and forth, but it is an oscillation in terms of electrons. Electrons that move in one direction and then reverse direction, move the other direction. It is still an oscillation, but it is an oscillation in the current. It's an oscillation in the movement of the electrons. It's an oscillation in the movement of the electric charges. Okay. So that's what I have for now for this chapter. We're going to talk more about it. Let's take our break right now. Any questions about that? till 10:25, break from 10:10 a.m. to 10:25. Okay. So I see you in 15 minutes. Uh-oh. Okay, so we're back here, and let's take a look at some simulations of the electric and magnetic field. Then we start getting to this, right? Into these consequences of the planar waves, electric and magnetic planar waves. Okay, so there is some, okay, let's see, not this one. Oh, okay, those are illustrations of the electric and magnetic fields, okay? In the three-dimensional space. We don't see the electric and magnetic fields like arrows, but that's how they look like. But there is a simulation. Let me see if Wikipedia has a simulation as well. Oh yeah, here you go. Simulation here. Here's a simulation of how electric and magnetic fields look like, right? We have the wavelength from peak to peak. The red should be the electric field. The blue should be the magnetic field. Yeah, you have here electric and magnetic, right? Oscillating back and forth. So those oscillations of the electric and magnetic field generates this planar wave. And don't forget, all those electromagnetic fields are being generated by a circuit that's far away. Can be a magnetic dipole, can be an electric dipole. Either one has, can generate the same type of electromagnetic field. There is another, let's see, Fendit. Yeah, Fendit simulations. I like this website here. Walter Fendit. He also has, he has several simulations here. And one of them is the electromagnetic wave, right here. Okay. So we go. Electric and magnetic fields. Can you speed that up? No, you can't. They are perpendicular to each other. Especially in the vacuum. In different materials, they're almost perpendicular to each other. This type of wave we call transverse electromagnetic wave. Okay, transverse electromagnetic wave. They're perpendicular to each other. And now, because of this variation of the electric and magnetic field, we have this illusion that something is moving along the positive direction of the axis. And in reality, it is this something that's moving is energy, okay? It's energy that's moving, that's propagating, energy that's carried by the electric and magnetic field. Do you remember in physics 38? Both the electric and magnetic field store energy in them. They do store energy. And now with an electromagnetic wave, this energy can be transported from one place to another, just like the sun does with the earth, right? The sun emits electromagnetic waves, and the energy that comes from the sun travels through space and reach Earth and the other planets. And this energy can, if we are smart enough, we can convert this electromagnetic energy to do some sort of useful work. Okay, so things to know. Okay, things to know. No. In vacuum. One. In vacuum, the electric and magnetic fields of an E&M wave are perpendicular to each other. Okay. We say that the wave is a transverse electric and magnetic wave. No, transverse electromagnetic and electric and magnetic waves, abbreviated by the expression TEM. Just keep in mind that if once you start studying, right? Just for the fact that I'm telling that there are transverse electromagnetic waves, there are also transverse electric, and there are TM waves as well, transverse magnetic waves, but that's for a more advanced course, okay? Keep that in mind for future. And then there's also hybrid waves, you know? The speed of an of an E&M wave in vacuum, the speed of light. Now we can start saying that we have a planar electromagnetic waves. And a planar electromagnetic waves is given by this relation here. Right? Given by this relation. The parameter K inside is the wave number. And let's write it down. K here is 2 pi over lambda. But let's not forget that there is a relation between lambda and the frequency, right? Remember the speed of the light? The speed of the light is going to be lambda times the frequency, or divided by the period. So you can here write that equation in terms of the frequency. Oh boy, here you go. Lambda is P divided by F. Okay. And then K becomes K becomes 2 pi F divided by C, or omega divided by C, okay? So the parameter K inside the planar wave depends on the frequency of the magnetic dipole antenna. Okay. Consequently, the frequency of the wave depends on the frequency of your circuit. Okay? The velocity of the wave is c. X and t are independent variables. And let's see if we can find out the amplitude of these two waves, okay? If there is any relationship between those two amplitudes. Let's do that, and then we talk about the types of electromagnetic waves too, okay? There is a way to find out the relation between those two amplitudes. A very straightforward way of doing that. And how do we do that? Let's go back to those two relations here. Those two relations here. I'm starting here with the EDX, okay? EDX is going to be something like that. The sine becomes a cosine, right? With a K in front of. And then minus dB dt becomes cosine, right? Times minus CK. So we have this one and this one. Okay, that's what we have here. And negative with negative cancels out. And look what we get. We get a relationship between the electric and magnetic field amplitudes. The magnetic field is going to be the amplitude of the magnetic field is going to be the amplitude of the electric field divided by C. Very nice result. We get exactly the same thing if we use the other equation. So we use this one first, right? And then we use this other one here. Exactly the same thing. So now my planar wave can be something like that. What else we have to know? Okay. I'm going to put the K in terms of the frequency, okay? The angular frequency, right? Here you go. Angular frequency here, angular frequency here. And let's not forget this angular frequency is related to the frequency, okay? Different frequencies of oscillation of your circuit, your electric circuit, give rise to different types of electromagnetic waves. Okay. And then we can start talking about different types of electromagnetic waves right here. So you see here what we have. What we have here is an electric dipole antenna. Okay. I illustrated only a magnetic dipole antenna, but you can also have an electric dipole antenna that's going to generate electromagnetic waves. That's a representation of electromagnetic wave. Okay, like a circular waves. And here you go. Oh, here you go. Here's the electromagnetic spectrum. Okay. We have this electromagnetic spectrum. That's a huge spectrum. It goes from what you have here at the top are the wavelengths, okay, of the wave. What you have here at the bottom is the frequency. Frequency of 10 hertz, 100 hertz, 1,000 hertz, 10,000 hertz, and so on. Okay. In order to calculate the wavelengths, all you have to do is divide 300,000 kilometers per second by the frequency, and then you get those wavelengths. 10 hertz is around a wave of 10 to the 7 meters. Okay, a little bit more than 10 to the 7 meters. The higher the frequency, the shorter the wavelengths. Why is that? Because the frequency is inversely proportional to the wavelengths and directly proportional to the speed of the light, right? So we have here this, on the extreme left, we have long waves, radio waves, infrared waves that was discovered by Herschel. And then the visible spectrum that is just a very small window in the electromagnetic spectrum. We cannot see anything. We're blind. Basically, we poor human beings, we're just blind. We don't see, we see just a very small fraction of the electromagnetic spectrum. And then we have ultraviolet waves, X-ray and gamma rays. The most energetic electromagnetic wave is the gamma rays. The least energetic is the long waves. Now we go back to that derivation that we got for the power of a wave. Remember that? Going back here. We did that just now. I'm gonna go back and go back here. Just before, oh, right in here, the power of any wave, right? Magnetic waves. From the radio waves through microwaves. Microwave is just a type of radio waves. Through the microwave, infrared, visible light, ultraviolet light, X-rays and gamma ray regions of the electromagnetic spectrum. Okay. Going back here to the power of the wave is directly proportional to the frequency, right? Angular frequency, by the way, is going to be like that. Frequency, and is the square of the frequency and the square of the amplitude. And now you know why gamma rays has more energy, right? Than is this one here that I want. Okay, gamma ray has the most energy than the other waves. This type of waves here are called ionizing radiation. That's another name for the electromagnetic wave, radiation, right? Ionizing radiation. There's X-rays and gamma rays have so much power. Oops, the frequency is right in here. There's so much power that they can ionize substances, can ionize substances, okay? And here you go, maritime and aeronautical uses. People use this region of the spectrum to communicate, right? AM radio, the radio that we have used this region of the spectrum. Maritime, aeronautical, and mobile radio. Mobile radio is our cell phone. This is the region of the spectrum. And then we have FM radio, TV channels, right? They allocate every, a little bit of this, all those slices for different regions of communication. You go and 10 to 11, see that? 10 to 11 goes all the way down here. So communications allocates the wavelengths, the frequency for communication is allocated between 10 to the 4th and 10 to 11 hertz. Make sure you don't use X-rays and gamma rays, right? Because they're gonna fire, you're gonna fry whoever is listening to your communications. Okay, red has a lower energy than blue and violet. Consequently, it has a longer wavelength. Okay, here's the distribution of light due to the sun, okay? Actually, the relative sensitivity of the average human eye to electromagnetic waves. We evolved to have this type of sensitivity because the sun emits most of this light of its light in this region of the spectrum. Okay. Go. And so using Maxwell's equation, we prove that the electromagnetic field obey the wave equation, right? We also prove that E and B are perpendicular to each other in vacuum only. E and B in terms of a planar wave. For simplicity, we assume that the amplitude of this E and B do not decay. Okay, this is an approximation, right? So within a small distance. In reality, they do decay as you move further and further away from the source. And we found a relationship between the amplitudes of the electric and magnetic fields. That's what we have here. And now we can start talking about the energy that the electromagnetic wave carries. The energy density. And that all comes from your course in electromagnetic theory, physics 38, right? It's a very easy equation to memorize. Just remember the equation for the kinetic energy is half of something times something else. For the electric field, the energy density is going to be given by half epsilon naught E squared. Epsilon naught is the electric constant, right? The magnetic field is something similar, but the difference is that the constant, the magnetic constant, is going to be downstairs, and it's still going to be B squared. That's what we got from physics 38. Let's see how they compare. Okay, B is equal to EM over C, right? And we compare, here you go, UB mu sub B, okay? 1 divided by mu naught, E over C is squared. That's for the magnetic field. That's for the magnetic field. Okay, don't forget, all that stuff here that you're seeing is a function of T, right? The function of T. And X too, right? X and T. X and T. X and T. I expand, and then, here you go, here's the energy density of the magnetic field. C square is equal to mu naught epsilon naught, see that? And look what happens, the mu naught cancels out, and we end up with the same energy density. We end up with the same energy density. I'm gonna put a function of X and T here as well. Okay. Okay, for then we can write down that the energy density of an E&M wave, right, is gonna be just twice the energy density of the electric field, which is epsilon naught E squared. So we have that in the book as well. Electromagnetic waves, okay, energy transport and the Poynting vector. Okay, so one more thing before we get, let's see, reflection. They don't have the energy, right? Oh, energy. Yeah, here you go, energy transport. We're gonna get into that, and the same thing. He's doing the root mean square here. What about the energy density? Yeah, here you go. He didn't do, yeah, doesn't look like he did the same thing that I did, but we'll get there. So one important thing that I didn't mention that has to be mentioned, okay? Direction of propagation of an electromagnetic wave. The direction of propagation of the electromagnetic wave is given by the cross product between the electric and magnetic field, okay? Electric and magnetic field. So let's take a look at that simulation that you saw. Okay, take a look here. This wave is propagating from along the positive direction of the x, right? But if we stop the simulation and take the the cross product of E with B, you're going to see that cross product of E with B shows the direction of propagation of the wave, of the electromagnetic wave, okay? So I'm gonna put here, I'm gonna write down as a vector. Direction of propagation means the velocity of E&M wave is proportional to, yeah, not equal, but proportional to E cross B. Okay. And this quantity is also referred to as the Poynting vector, which we abbreviate by the letter S. Okay. This is a proportionality symbol. Okay, and that's what let's see how the Poynting vector is defined. Here you go. The Poynting vector, okay. Okay, here you go, it's defined like that. Specifically speaking, right? Let's go to magnetic wave. Now we gotta blow it up. 1 mu naught. Okay. One divided by mu mu naught. Okay. And because those two fields are perpendicular to each other, so let's say the E, I get the left here. Suppose that the E field is pointed in the x hat direction, right? Okay, and this, oops, no. This one here. Like that. And the B field is in the y hat direction. No, hat. Good. Now we can write my Poynting vector as being in the z hat direction. X cross y. Like that. M squared, right? This one goes away. My C becomes, let's put the C down here. Oh, it should be sine of square as well. And we see. And can we do better than that? Let's see if we can do better than that. The C is going to be the inverse of the square root of epsilon naught and mu naught. Take away the C. And then we end up with a ratio in the square root, right? Square root ratio. Let's see here. Yeah, because this mu naught cancel out to this mu naught, right? Because this mu naught is in the square root. So what's left out is something like that. That's the Poynting vector. And that's the unit of the Poynting vector, right? And so rainbow, let's take a look here. Here's what I did, right? Yeah, the same thing that I did, okay, for to prove that Maxwell's equation is reduced to the wave equation. And here you go. Is what's the Poynting vector? Is the rate per unit area at which energy is transported via electromagnetic wave. Okay. So rate per unit of area at which energy would be watts per meter square. Okay, that would be watts per meter square. Let's go. watts per meter square. And gotta do dimensional analysis of this term right here. Unit of electric field square, and those two units here divided by one by another, okay? So an electromagnetic wave has energy. That's an important result here. An electromagnetic wave has energy. And if you're smart enough, you can tap into this. You can create a device that can tap into this energy. It's the case, for instance, of solar panels, for instance, right? And trees too, they are very good solar panels. Trees, algae, there's some algae out there that can use the electromagnetic spectrum to produce energy. But what about momentum? Does an electromagnetic wave also have a momentum? Okay, the answer is yes, okay? And the easiest way to understand the momentum due to electromagnetic wave is through the special relativity. We cannot derive that with the knowledge that we have here. It requires knowledge of special relativity, theory of special relativity. Okay? What Einstein had found out, when we are going to derive that as well, is that the energy of any particle, okay, whether you have a mass or not, the energy square of the particle is going to be c squared p squared. C squared is the velocity of the light, and p is the momentum of the particle. If the particle has mass, then you are going to have an energy component due to the mass as well, due to the rest mass. That will be the energy due to the rest mass. Okay. For a particle that is at rest, the momentum is equal to 0, and we are left just with this form, with this Einstein's famous equation, okay? mc squared. But if the particle has no mass whatsoever, just like in the case of the photon that make up the electromagnetic radiation, we have this relationship between the energy and the momentum. Ideally, we should write down at E, okay, but let's leave at U. And here go. That's the relationship between P and the energy of the particle, the momentum and the energy of the particle, okay? So the force, the electromagnetic wave imparts is going to be delta P over delta T. Okay, and the pressure is, you already know, is a force divided by area. If you can change the momentum, right? You can apply force to an object. If the momentum is not changed, then there is no force there to apply. And one way, and so how can we change the momentum of electromagnetic radiation? Okay, we can use a mirror. Light comes one way towards the mirror with a momentum in, let's say, to my left direction, gets reflected. Initial momentum is to the left, final momentum is to the right. Okay? And if we do that, here we go. final momentum minus initial momentum. We are assuming at 100 a mirror that is 100% reflective. Use a mirror. You go. Assume a mirror that's 100% reflective. If the mirror is 100% reflective, then the magnitude of the momentum is not going to change. And the difference between the change of momentum is going to be twice the initial momentum. Okay. That's what we have. And so it's 11:05 right now. Let's any questions about that? So I'm gonna save this document here and let's take a look at what we covered so far. Okay. Okay, 33.1. We have covered so far, right? Covered so far. No, 33.1. 33, no, 30, yeah, 33.1. We cover a little bit of energy transport and the Poynting vector. We didn't, a little bit of energy radiation pressure. Didn't cover polarization yet. Okay. And then we have reflection and refraction, total internal reflection, and polarization by reflection. We didn't do that yet. Okay, so so far we have those three covered. This one is electromagnetic waves, right? So electromagnetic spectrum from just a summary what we have done. Electromagnetic spectrum. Electromagnetic spectrum from radio waves to gamma rays. Okay, energy of an E&M wave. Okay, plus the Poynting vector. Poynting vector, which tells us tells us the direction of propagation of an E&M wave. And we look at the energy of a wave. That's 33.3. Energy of a wave and its relation with the linear momentum. Okay. And a change of momentum gives rise to a force, right? That exerts a radiation pressure. And again, radiation here we mean electromagnetic waves, right? It's radiation is an interesting word. It's used to both to describe electromagnetic waves and particle waves that comes from the nucleus of an atom. So make sure that you understand that difference, right? I'm going to write that down here for you. Radiation is a funny word, right? That describe both an electromagnetic wave that's transmitted by massless particles and nuclear radiation that is due by particles that has mass. Okay. Let's take a look at the dictionary, what dictionary states here. So keep that in mind every time that you hear radiation, what it exactly means, right? It can mean either one or the other. In the case of this chapter, radiation in this case refers to electromagnetic radiation only. You go the emission of energy as electromagnetic waves or as moving subatomic particles. Okay, especially high energy particles, which cause ionization. So radiation can be due to massless particles and particles that have a mass, especially due to high energy particles, which cause ionization. So it's not just X-ray and gamma rays that cause ionization, but also particles that have very high energy. They also cause radiation, just like neutrons, for instance. Okay. And we're coming to a point that I want to get a break. Okay. How are you doing there? Any questions so far? Don't forget the exam, right? Next Thursday, 1 week from now. Exam 1 week from now. And summary. I mistype it here. So let's get our break. Now, what I want to do, let's get our 30-minute break for lunch, right? So that's going to be 11:15 a.m., right? To 11:45 a.m. Good enough. Then we meet again in half an hour. Okay, see you in 30 minutes. Okay, I'm back here. So what I want to do now, it's very important that you folks get familiar with this quantity, okay? And like I mentioned before, the unit of, like the book mentioned before, right? The unit of this quantity, that's something, that's a unit that we create out of by nothing, right? But which ends up to be a very important unit. And no, I want to prove that the unit of this quantity, the Poynting vector, is the watt per meter square, okay? What I want to do, so we're going to start with this equation here, because we are talking about just the unit of the Poynting vector. Okay, the unit of the Poynting vector, which gonna do just dimensional analysis, right, is going to be the unit of everything here in this ratio. Let's see if it really reduces what the book says. I prefer to use this one here because we know what the unit of C, right, and mu naught. So what you see here upstairs is the unit of the electric field squared. What you see here downstairs is the unit for speed. And then we have the unit for this constant as well, the permeability constant. I will put everything like that. And then let's break down those units one by one. The unit of electric field is nothing but the unit of newtons divided by the unit of coulomb. Since we are talking about the square of the electric field, we end up having Newton square per Coulomb square. The unit of speed is meter per second. And I want to keep those units separately. And then we have to look at the unit of Newton, right? Let's take a look at the internet. Unit, let's see. Yeah, that's right. Let's yeah, there are several ways of spelling out these units, right? So one of them, right, is this one that you're mentioning, and there's this other one as well, which is Henry per meter. Henry per meter. Okay, and let's simplify everything. It's just a regular algebra, right? The meter here is going to cancel out with the meter here. So I can pass my second upstairs. And I will get rid of this. I didn't do anything wrong. Everything should be right, right? And then the unit of Henry. That's our next unit. Unit of Henry is going to be, there are several ways of writing down the unit of Henry. One of them is a kilogram meter square per second square amps square. Yeah. And what I'm going to do here, I'm going to break down this Newton square into newtons, okay? And let's going to move the next one. Amps square times second square is going to be Coulomb square. And the Newton here is going to be kilograms meter per second square. All right, and then we go to the next step. Kilograms cancel out with kilograms. This Coulomb square cancel out with this other Coulomb square. Meter square still here, and then I'm gonna put my second square here. And by the way, it's gonna become seconds, right? Because it cancels out with this one here, and we have meter. By the way, look what we are getting here. Oh, whoa. We're getting Newton meters upstairs, right? Newton meters upstairs is what I'm not going to cancel the meter with the meter. Newton meter is going to be joules. And then I'm going to put the seconds upstairs so you can recognize the joules per second being the watts, right? And here you go, watts per meter square. That's exactly what we saw here. Okay. Well, let's play a little bit more with this guy, right? With this Poynting vector. Let's work a little bit more with that. Let's not forget, here you go, I'm gonna copy, I'm gonna put it here. Let's see, no, I don't want that, I want this one. I want this one right in here. Okay. So that's the instantaneous flow of energy. Okay. And notice that it changes with time and changes with position as well. But it's in general, we don't want something that changes with time. You know, in general, we don't like quantities that change with time. For this reason, you usually average them out, average them out. Average them out, right? Now, this quantity averaged out in time, okay, I'm gonna put S, and now I'm gonna deal with, not with a vector, but with a scalar, AVG. This quantity averaged out in time, there is no more need for a vector because we're dealing with a scalar. Is going to be the average. When I put this guy between parentheses, is going to be the average of the sine of square. Sine square value. Which, by the way, can be calculated over the period of this wave. We end up getting 1 divided by 2, okay? Like that. Any sine square of theta average out over a full cycle is going to be half. And you remember the definition of root mean square value, right? So what you end up having here is nothing but, you go, okay, it's nothing but something like that. Okay. And whatever is inside this parenthesis is that quantity that we learned in electricity, right? Electricity and magnetism, which is, oh gosh, see what I did here? Yeah, but root mean square value, the square of the root mean square value of the electric field. If you want to, you can even leave this way, right? Or if you're more familiar with the root mean square value, you leave this way. Now let's do a example, right? We have been doing this example. (33.2.1). Okay. We have the star, the North Star, Polaris. Emits energy at a rate of 2.2 times 10 to the cube times 2,200 times that of the sun, which ends up being, that those are given values, okay? Values given by the problem. That's to the cube. Superscript. Watts. Okay. Find the RMS values of the E and B fields. Okay, and I'm going to solve that, right? That's going to be 6.6 times 10 to 29 watts. 29 watts here. And see. Oh, by the way, we also have to say that Polaris is at a distance of 431 light years. Huh? There's a missing information here. Missing piece of information. Well, let's see here. One more thing that I was supposed to tell you. Before we go for this problem, right? So for this problem, is that there is another quantity, important quantity, that is the intensity of the wave. Okay, and the intensity of the wave is exactly equal, to the average Poynting vector. Okay, if you hear about the intensity of a given wave, electromagnetic waves, think in terms of the Poynting vector. But there is one more thing. There is one more important piece of information. Okay. Yes. The electromagnetic waves that reaches us, okay, the E&M waves, we're doing an aside here before we do the example. The electromagnetic wave that reaches us is due not to a static, it's not due to a static field. I'm going to put it here. It's not due to a static, electric, or magnetic field, okay? Very important that it is due to a induced electric and magnetic fields. If you go back with in your electricity and magnetism course, I want you to remember the first type of electric field that we saw, right? The first type of electric field that we saw was that of a point charge. Remember that? And the electric field of a point charge was equal to what? It was proportional to what, right? It was proportional to the square of the distance. That's the easiest type of electric field that we have seen out there. And then, we look at the dipole, electric dipole as well, right? And then we obtained that for very large distances, that the electric dipole, the field of the electric dipole, electric field of electric dipole was would go down with the cube of the distance. Okay, the same thing was for the magnetic dipole, P dipole. And then there were other types of fields that we called electric quadrupole, right? I covered that with my students, which goes down with the force power of the distance and so on. Okay. And then, those are fields, those are static fields. What do I mean by static fields? Fields that fields due to sources that do not change in time, right? For the electric field, the source is the charge. That's a constant. For the magnetic field, the source is the current. That is also a constant. However, if any of those sources change in time, something else happened. Okay? Something completely different happened. And it's also surprising. Completely different and surprising, okay, happens. Okay, so it's possible to prove, and I remember that, and make sure that you saw that, you remember that. And an induced electric field, it doesn't go down with the square of the distance. It's something better than that. It goes down with the inverse of the distance. We still have a functionality here in terms of time, but just the fact that it goes down is lower than the other fields is a big advantage. Okay? So it is this type of field and that we are detecting. And by the way, it's not just the induced field. It's the induced electric field. It's also the induced magnetic field. It goes down with the distance. So everything that I wrote here, is not completely correct. Okay. This electric field, it doesn't have a constant amplitude. It actually is an amplitude that's decreasing with the inverse of the distance. Okay? Especially if you are very far away. Because of that, when we square the electric field here in my Poynting vector, right? When I square the electric field here in my Poynting vector, I'm getting a drop with the square of the distance. And that applies also to the intensity. When you take the average, that also applies to the intensity, okay? Since the Poynting vector, Poynting vector depends on the square of the E field, it must decrease with the square of the field as well, which is far better than decreasing with the square of this ratio, far better than decrease with the square of this ratio, and so on, okay? So consequently, both the intensity and the average Poynting vector must decrease with the inverse. That's just another way of looking at that. Your book does different, okay? Your book does it slightly different. Specifically, this intensity is going to be given by the square of the root mean square value of the electric field divided by C mu naught, like that. Okay. Another way of writing that is going to be the power of the source. Okay. The power of the source, which by the way ends up being divided by the area, right? 4 pi r squared. And again, this r squared comes from the fact that we are dealing with the induced electric and magnetic fields. Okay. And now we can find out what is the root mean square value of the electric field, of the electric and magnetic field from this equation here. Okay. So here we go. We will use this equation right in here. And solve for the root mean square value. C mu naught and then we take the square root. Square root of that. Okay. And then just a matter of plugging in the values in there, right? And you end up getting what? 1.2 millivolts per meter. 1.2 millivolts per meter. It's that's a measurable voltage, okay? 1.2 millivolts is measurable voltage. Remember, this is milli and this is meter, right? And what about the root mean square value of the magnetic field? Root mean square value of the magnetic field. Can you remember that? That's not difficult, right? Remember, it's going to be something like that divided by 300,000 kilometers. 302 million meters per second. 23 meters per second. Oh, no. Meters per second. Okay. And that's going to be very low value. If you do the math, you end up getting a very small value. According to the book, it's 4.1 picotesla. Picotesla is 10 to minus 12 Tesla. I can even write that for you here. It's those values are so small that's difficult to detect. This one is not that difficult to detect. Multimeters can get voltages on the millivolt range rather easily. But picotesla would be a big challenge. Okay. .2 millivolts, yeah, it is small, but 1.2 millivolts we can detect with a multimeter. No, I have multimeters here. Let me get my multimeter here. Yeah, that has a scale in millivolts, by the way. Okay. You can, by the way, we cannot compare, a magnetic field with an electric field, but this is very difficult to detect. That's what we have here for this. I'm gonna save this one. And the R, the R that you see here is gonna be 431 light years. That the value that you use there. Okay, 10 to 18 meters. So the magnetic field in the electromagnetic wave of a star that is far away is more. And see, let me see one thing here. Do you understand this part here of the Poynting vector? Okay, we assume that is a planar wave, but in reality, is a planar wave that's decreasing as distance goes by. Okay, and that is due to the fact that induced electric field goes down with the inverse of the distance, and that's not bad at all, because if we were to detect the electric field due to a static electric charge, the Poynting vector of the static electric charge will be, when you divide by the 4 power of r. Here would get 1 to the r square, right? Because the Poynting vector is the square of the electric field, electric and magnetic field. Okay. Now going back here. 25. The radiation pressure, right? So let's go back. Here you go. That's, oh, here you go. That's what I was looking for. Okay. So let's continue this relation here that we're talking about. Let's just remind you what's happening here, right? We're talking about momentum, linear momentum of the electromagnetic wave. Now we know that it has energy, and now it also has momentum. If it has momentum, it can apply a force, okay? If electromagnetic waves have momentum, it can apply a force to an object. And just recently, people demonstrated it in the lab. Okay, I remember getting a video of a device being propelled by a laser. And they put this device in a air track to decrease the friction, and put a little screen that would reflect the light from the laser, and little by little that device started to move forwards. Okay, but even before this experiment in the lab was done, people has launched objects in space that were propelled by the rays of the sun as well. I used to work at NASA, and there was a group there at NASA that deployed exactly something like that in space. It was a huge spacecraft with a solar. It was propelled by the sun rays. It was a mylar. It was a screen made of a mylar. Okay, that was huge. And they could see that it was being accelerated to higher orbits just by propulsion of just because of the radiation pressure of the sun. Okay, and everything comes from this, and this can be explained in terms of the relativity theory of Einstein. Okay, yeah, maybe I can find that at just at the time where we had the Mir space station there. I believe it was back in the 90s. Okay, solar cell they would call it. Thank you for the feedback there, Alexis. Let me see if I can find that. I was at NASA Langley when people did that, and then later on I discovered that it was this guy that was used to work in the second floor that managed to get money from Washington, the headquarters, right? NASA headquarters, to do the same. And they got lots of money to do that. But I found that out only after the fact, unfortunately. I asked him why you didn't hire me for that, right? Solar cell, let's see. Solar cell spacecraft. Okay. A method of spacecraft propulsion using radiation pressure exerted by sunlight or on large surface. A number of spaceflight missions, see that, to test solar propulsion and navigation have been proposed since the 80s. The first spacecraft to make use of technology was Icarus. Yeah, but there was that other people there at NASA that did that too. I do not know why they're citing only those guys here. Icarus from Japan Space Agency. Laser beams, history of the concept, Johann Kepler, James Clerk Maxwell. See that? James Clerk Maxwell, when he derived the equations for electromagnetic waves, he starts thinking in terms of momentum of the wave that can be exert pressure, but he still didn't have he didn't know about relativity theory, right? So he had to derive that in other ways. So Maxwell's equations provide the theoretical foundation for sailing with light pressure So by 1864, the physics community and beyond knew sunlight could carried momentum that would exert pressure on objects. Jules Verne, there will be some here publishing From Earth to the Moon. He explored this possibility as well. Light mechanical agent. Okay. Lebedev, Sven Arrhenius. I want to see Haldane, Arthur Clarke. Okay, Arthur Clarke wrote a science fiction novel, short story. By the way, I read the story of his. And what about the history? Okay. Unfortunately, they don't have here history of concept. They don't mention that. Yeah, I wonder why. Electric cell, probably solar wind. See solar wind. Let's see electric cell and magnetic cell. Electric cell. That's the solar wind. Okay, NASA Marshall Space Flight Center. Yeah, I will. I cannot find it now. Unfortunately, they don't have a citation about that group there at NASA. Rendering. First, intrinsic limitations. Let's see. Yeah, unfortunately. NASA solar cell. Let's try another one before we move forward. NASA solar cell propulsion. Since the 80s, NASA. Sunjammer, is this the one? Flight tested. Yeah. What about solar cell? Let's see, Mir space station. Mir space station. They also deploy it. I'm surprised they are not mentioning that solar cell propulsion. Let's see. Okay, I will have to look with more carefully. I cannot find it now. This Mir, MI, maybe it's Mir space station. Mir space station, solar cell propulsion for interplanetary. Let's see. This solar cell propulsion for interplanetary small spacecraft. Let's see where they mention about Mir space station here. Brief history of solar cells. This is an article. This is a paper. Okay, and where is Mir space station? Now the Marine spacecraft. I have to go back here. After, okay, the Russian Space Agency conducted the first in-space solar cell deployment from a Progress resupply vehicle after it undocked from the Mir space station. Yeah, that's what happened. And that was back in the 90s, okay? And then those guys there at NASA did the same thing. Let's see, Mir. No, okay. The Russian Space Agency conducted the first in-space, 1993, okay? The first in-space solar cell deployment from a Progress resupply vehicle. The Russians still have this Progress vehicle. After it undocked from the Mir space station in 1993. Isn't that funny that the other articles doesn't mention that? Called Zmaya. The cell deployment was successful, right? In 1999, the second Zmaya solar cell collided with a deployed spacecraft antenna and was shredded. Too bad. Okay, so yeah, that happened. And they made a reference here. Sky and Telescope. Have you heard of Sky and Telescope? Okay, it's an astronomy magazine. Famous astronomy magazine. So yeah, back in the 90s. I'm surprised that Wikipedia didn't mention that that experiment that they performed there with the Mir spacecraft. with the Mir space station, right? Let's move this one here, so it's not in your way. %10 of speed. Oh, yeah, that's right. Yeah. And yeah, 10% speed if propelled long enough, right? But how far away was that from the sun, right? You got to look at how far away it would be from the sun. I like this. So did you assume that how far away did you assume that the spacecraft was from the sun when you reached this conclusion? Okay, yeah, it has to be pretty close, but it doesn't matter, right? It can be far away from the sun because it's accelerating all the time, right? It's accelerating all the time. And by the way, ion propulsion can do those things too, right? Ion propulsion propel a spacecraft at very low acceleration levels, right? Since the momentum of the particle decreases when they get further. Yeah, that's right. The momentum. It's not that the momentum of the particle decreases. The momentum of each photon remains the same, right? The problem is that you don't have as many photons colliding with your cell. That's the problem. The area, right, that is collecting, is becoming further and further away, right? And the photons become dispersed as you move further and further away from the sun. Okay, that's the reason, not because of the momentum. The momentum of each photon doesn't change, but the amount of photons that reaches your cell changes, okay? The amount of photons that reach your cell decreases as you get further and further away. Okay, that's interesting. Okay, and 10% of the speed of the light is a lot. Yeah, that's right. Okay, so let's go back here. Here you go. Here's the relationship, right? Between the energy and the momentum. And if you want to change the momentum, you must have a change in the energy, delta U. And that's for total, let's see. That's for the case of total absorption, by the way. Right, so here you go. For total reflection, where's the equation? Here you go. Here's the equation for total reflection. And I shouldn't be writing that, okay? I shouldn't be writing that. I shouldn't be writing that here. So total reflection, right? 100% reflection. We get this relationship, right? 2p. I'm going to just work with the and we end up with U divided by C, right? Total reflection. Now, if it's not total reflection, if it is not total reflection, but total absorption, how total absorption works? Two limiting conditions, right? The final photon momentum is 0, right? And by the way, this is the 0 vector. And the initial momentum of the photon is P0, right? And then we end up getting with just P0 here. And instead of 2U over C, you get 2 over C. Total reflection back along the path, total absorption of the photon. Total absorption of the photon, okay? Okay, and now let's see if we can relate it, the force applicable to that, determine the force, right? Due to this change in momentum, right? I wrote down the force here. No, I didn't. So the force is delta. Oh, I don't like that. Delta, yeah, gosh, okay. Well, italicize the saying. Good. Delta P over delta T. Okay. And let's see, this one doesn't belong here. This one belongs. Okay, belongs elsewhere. Belongs right here. So you have here a relationship for delta P, right? Under two different conditions. But what about in terms of the intensity, right? Remember what intensity is, right? Intensity is power over area. Power over area. Or energy, right? Energy per time over area. But by the way, from this relationship, okay, we can call the energy my delta U, right? Which is going to be divided by delta, oh, no, delta T. Delta T. And I'm going to call the area A. Going to the next level here. We get delta T downstairs. Italicize them so it looks better. Okay, and we solve for delta U as being IA delta T. Something like that, okay? But let's not forget, right, that this delta P here is also, can be also be here written as delta U over C. And do you see that I will have a delta T right in here? We do not know what delta T is, right? Yes, but if we use this equation for the force, the delta T goes away. Some of those lucky circumstances that we find in physics every now and then. Okay, and now we get that that the force applied to your spacecraft depends on the intensity of the radiation and the area of your spacecraft. But that's for total absorption, right? For total absorption. total absorption. That's for total. Now, if we want to do the same for total reflection, we have to multiply that previous result by 2. Okay? And it's divided by the speed of the light. Because the speed of the light is very large, right? It's very difficult to come up with a strong force. But it's still is measurable. The force that can be measured. If you're in space and you don't have any drag in your solar cell, is very large. Okay, I want let's take a look. We have that paper, right? Let's take a look at that paper again. See if I can find it. Your space station, solar cell. Okay, 1993. So that was the experiment with the Mir space station. Later on, that guy at the NASA also did this experiment, and people could see the solar cell by naked eye. By the way, at the time, you know, we could see the solar cell that the Russians deployed by naked eye until a certain moment, which was very, very nice to follow it. Fast of travel. Could any human survive that fast of travel? I think so. I think so. The problem is how we're going to load your spacecraft, right? And keep all the environmental supplies for humans there. That's the challenge. That's the challenge, right? Hopefully, Elon Musk is going to be able to do something like that in the near future. Elon Musk and the other billionaires. They're all planning a trip to Mars, right? If okay, now we can do something else too, right? Notice that my force here is directly proportional to the area, right? But what about the pressure? The pressure is going to be a, I gotta put P, capital P, right? The pressure is going to be a simpler equation, okay? That's for total reflection. We have for total reflection. We have something like that. And now it would be nice to find out what would be that pressure, right? Let's take a look at intensity, solar intensity, right? Solar intensity of the Earth's orbit. Earth's orbit. Don't forget, solar intensity is watt per meter square. Okay, let's go here to the Wikipedia. This is sun rays. Let's see here. The average intensity of solar energy reaching the top of the atmosphere directly facing the sun is about 1360 watts per square meter. Okay. That's what is the intensity at the top of the atmosphere, of Earth's atmosphere. You know, find the pressure, the radiation pressure. You know, solar intensity at the top of the Earth's atmosphere. is 1,360 watts per square meter. Find the radiation pressure at this point. Don't forget that's average. Average intensity, right? Solution. Yeah, that's a solar pressure. Go and 1,306. Oops. Times, right? Times 1,306 watts per meter square. Square and divided by 300,000. 300,000, no, 300 million, right? 1, 2, 3. 300 million meters per second. Put the commas in there so we don't lose track. And what do we get? And what do we get? It's gonna be a small number, right? I'm gonna go to my Excel spreadsheet. And that's under the best of the circumstances, right? With total reflection. 300 million. 1, 2, 3, 1, 2, 3. Okay, that's Newton per meter square. Micro Pascal. 9 micropascal. Did I do it right? 1,360. Watts per meter square, right? Divided also by meters per second. I'm gonna put my 2 here. Meters per second, everything here. Superscript. It's better if you do elsewhere, right? Because that's the unit. And let me get this number. 9 times 10 to the 9. Okay, it's not difficult to memorize. Let's go. 9 times 10 to minus 6, right? Watt per meter square, meters per second. Did I do something wrong here? Doesn't look like, right? Here is joules per second. Joules per second cancel out with the other second, right? Here is going to be Newton meter. Meter cancels out with meter, and then look what we get. Makes sense, right? We did apparently we did everything right. And that should be Pascal. Now, if you want as large as a force that you want to have a very large cell. Very large cell. And I'll be interested in finding out what would be the dimensions of the solar cell. Dimensions of a solar cell, right? What you're talking, oh, here you go. NASA team in the 70s headed by Planet co-founder Lucy they proposed. Okay, 600,000 square meter. They proposed that would be used to send a spacecraft to rendezvous with Halley Comet. Yeah, but what about measuring up solar cells? Right now, NASA is testing 2 competing 20-meter solar cell propulsion system. That's small, isn't it? Advanced composite solar cell. Yeah. Crossing the solar line is 400 square kilometer solar cell. Okay, 400 square kilometer. Oh man, well, are they building that or they're just dreaming about it? Let's see. Crossing the solar system on a 400 accept all cookies, right? Those 400, man, it shouldn't be difficult to deploy that, right? If you get some Mylar sheets, you can, fold them, and then when you get into space, you just deploy them. Maybe that shouldn't be that unrealistic. Look at, I presume that that's the solar cell. No, that's the solar cell, maybe. ECL project is pioneering solar cell design that intercept charged particles in the solar wind. The idea developed by Pekka, Finnish Meteorological Institute. But it's a charged particles, it's not the photons, right? Yeah. The field will be generated by a 20-kilometer long aluminum wire. But let's use this. Let's use this value here. 400 square kilometers solar cell, right? Force. That force is going to be 9 times 10 to 6 Pascal, and going back there, I forgot already, 400 square kilometer. 400 square kilometer, 400 square kilometer. Square kilometer, right? Is going to be not bad. It's going to cancel out, 1 kilometer is 1,000 meters, so 1 kilometer square is going to be 1 million, right? 1 million square meter. And now we get this 1 million square meter canceling out this 10 to minus 6. And what's the type of force that we're talking about now? Now we're talking about a force, right? This one cancels out, this meter cancels out. Now we are no longer talking about the small forces here. We're talking about 3,600 newtons, right? 3,600 newtons in space with no friction whatsoever, but just at the height of the Earth's atmosphere. As we move further and further, it decreases, right? And then you can come up with your own acceleration. Let's see, what's the solar cell made of microscopic charged wire? A solar cell is could be one of the fastest ways to produce, as long as it's made of microscopic charged wires. Okay, charged wires here. The European Union funded ECL project. Micrometeoroids. What is the lightweight mission in the if the electricity program to work? Yeah, it doesn't give me ECL. Yeah, okay. We cannot go further than that, but let's go for our break, right? It's 12:52 right now. Let's, any questions about that? We can do more research on that, spend lots of time looking for and see. I was trying to look for the solar cell that they deployed there in the Mir space station. I want to know what was the size, but we cannot find much here. Light cell, image of dimension solar cell, versus spec, versus Wikipedia. Let's go back to Wikipedia. 800 meters, okay. 5 newtons. Now this one is 800 meter solar cell, must be diameter. Okay, so let's go for our break. Is 12 break between 12:55 p.m. and 1:10 p.m. Then we start covering something else. Okay. I see you in 15 minutes. Okay, so I'm back here, and there you go. Just before we move into actual material, right? I was looking more carefully about the solar cell here. Here you go. On February 4, 1993, the Zimaya 2, a 20-meter wide aluminized Mylar reflector. Mylar reflector was successfully deployed from the Russian Mir space station. It was the first thin film reflector of such type successfully deployed in space using the mechanism based on centrifugal force. So they put the device to spin, right? Although the deployment succeeded, they claim here propulsion was not demonstrated. I'm not sure if it's true. Okay, at the time we were saying that the spacecraft was going to higher and higher orbits. I remember that. A second test in 1999, the Maya 2.5 failed. And then you can go here to this link, right? 20-meter wide space solar mirror. That's the Zimaya spacecraft. Solar mirror, okay. Launched aboard. Actually, the spacecraft was a Progress, right? After visiting EO-12 probe aboard Mir space station, the Progress then undocked and deployed the reflector. See, that's the Progress spacecraft. They deployed the reflector from the end of the Russian Progress spacecraft on February 1993 next to the Russian Mir space station. The mirror deployed successfully, and when illuminated, produced a 5-kilometer wide bright spot which traversed Europe from southern France to western Russia at a speed 8 kilometers per hour. The bright spot had a luminosity of equivalent approximately that of the full moon. So this thing could have been done for a solar cell experiment, right? But instead they use it as a mirror. Okay, the Maya mirror had originally been designed as a prototype of solar cell propulsion system, but was repurposed as a space mirror for illumination when interest in solar cells flagged. And then they have this Icarus spacecraft from the Japan Aerospace Exploration Agency, right? That they claim to be the first one to use photon propulsion. And what I want to do now, let's go back. Here you go. The chapter that you have to worry, the section that you have to worry is all sections of chapter 15 and 16. So far, I cover only sections 3 and 5 of chapter 17, and you should worry about those 3 sections of chapter 33, okay? I want to cover another section. I want to go back to chapter 17 to cover beats. And don't forget, we jump in here because everything that we're doing here is on waves, right? Including electromagnetic waves. And now, going back here to this, what I want to do beats. Okay, it's a very interesting phenomenon. Okay, what is beats? I like to call beats interference in time. Okay, beats. And I will write it down here in the book. Beats 17.6. 17.6. I'm not going to cover everything in chapter 17, okay? Beats. Okay. Interference in time. So far we have been talking about interference in space. But what about interference in time? Let's see how it works. And there is a demonstration. There is even a demonstration I can make here for you. Okay. Consider this time we are going to combine two waves of different wavelengths, okay? Interference in space and waves having the same frequency, and we've had the same frequency and wavelengths, okay? In the case of bits, the interference will be in time, but and the wavelengths are going to be different. Okay? Different from each other. So the situation of the wave is like that. We're going to have two waves. Okay, I'm going to copy this one here. And just for the sake of simplicity, I'm going to have both waves. Here go the one wave here, y1 is going to have an amplitude A. Okay, I'm going to do is a cosine, and this wave is going to have these wavelengths 2 pi over lambda 1. The speed is going to be v, and the second wave is going to have the same amplitude, just for sake of simplicity. Otherwise, it becomes too difficult to solve this problem. We'll have a second wavelength K2. When we combine them, and then what are we going to do? We're going to combine those two waves. We are going to combine these two waves at the same position, okay? So it is as though as your computer is producing those waves, for instance, sound waves, and you're listening to them simultaneously here at a single position, okay? At the same position. So it is as though as x of 1 and x of 2 are the same. Okay? To make things simpler, this position will be placed at the origin of our coordinate axis. Okay, what do I mean by the origin of the coordinate axis? X1 equal to x2 is going to be equal to x, is going to be equal to 0. And then the equation becomes simpler. Remember, the coordinate axis can be placed anywhere we want, right? Oops. They're the same. And now that we did that, right? This becomes 0. And we get a minus K1 BT, which, by the way, doesn't affect my cosine function at all, right? So I can take this one out, and the other one's going to become similar to. The only difference being K2 VT. And now we're going to combine them. y, the resulting y of xt is going to be y1 plus y2. And I'm going to give you a demonstration. I want to make a demonstration of this beating phenomenon in case you haven't seen before. You haven't experienced it before, right? It's a really cool way of demonstrating physics. Okay, it's going to be something like that. What else can we do here? The wavelength is going to be different, right? And so will be the frequency as well. But because those are sound waves, I'm considering that as being sound waves, okay? The wavelengths can be different, but the speed doesn't change. I'm going to put those two in the amplitude in evidence. And what else can we do? The V, recall the V is going to be what? Lambda, by the way, it's going to be lambda 1, F1, right? And the K1 is going to be what? 2 pi over lambda 1. And then we have the same thing for the other one, for the other wave. Lambda 2, lambda 2, F2. And then lambdas go away. The wavelengths goes away, go. And we end up with the, oops, not the one, not the right one. This one here. We end up with the angular frequency, 2 pi f1, 2 pi f2. Then there is a little trick that you're going to do it, similar to that one that we did before. There are some trigonometric relationships that we can use that are rather useful for this type of problem. That's going to end up putting our equations in a more intuitive format. Suppose that we have two different angles, and we have the summation of the cosine of those two different angles, those two different quantities. What? How can I here write them? All right, there is an expression, a property. Here we go. We did something similar before. Cosine of A minus B divided by 2. Yeah. Times, oh, what is a summation becomes a multiplication. And then we can apply that to this one that you see here. A minus B. A minus B. A plus B. Let's see what end up happening. Okay, let's rewrite. I'm going to put, let's see, I'm going to do this way. Like that. I don't want to keep it there. I'm going to keep it here. So what is a summation becomes a multiplication. And when we look at this new expression, it becomes easier and more intuitive to understand it. Okay, so I'm gonna place those here in evidence. The 2 is gonna cancel out with the 2, right? Evidence as well. And one more step here, and we'll be ready to interpret those values. What I'm gonna do is just cancel this 2. Cancel that. And what else? I'm gonna put this one in front of the other. Okay. So notice what's happening here. Here we have a high frequency term, and here we have a low frequency term. Okay, if we plot something like that, let me show you what you get. You get a graph like that. Amplitude versus time, instant of time. Okay. What is high frequency? F1 plus F2 is this fast variation here in the amplitude, okay? Is this details inside this lobe. Do you see that? That's exactly what we get. We get this lobe formation here with a very high frequency signal inside this lobe, and those lobes are repeating with a lower frequency. That's exactly what we get. That's what we call beats. And when we start listening to sounds like that, you're going to see a very interesting behavior, okay? Think about this graph representing a sound, okay? So it is like listening to something like doo, 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 okay? That's instant of time. This signal has a period, and this is a period that keeps on repeating itself with the same interval of time. And this interval of time that you see here has to do with the lower frequency terms, here. Okay, so this lobe is controlled by this term, whereas the details inside the lobe is controlled by this term that has a higher frequency. Can you picture that? Okay. And we can go to the internet. And by the way, here you go, harmonic, right? Harmonic simulators. Simulation, maybe this one here. Let's see, vibration, harmonic assays, we have a site here in the internet that reproduces sounds, okay? Let's see if I can find where it is. Sound frequency. Similar sound frequency. Let's see. Sound wave simulation. Let's see, must be this one here. Next generation sound. The simulation lets you see sound waves, adjust the frequency or volume, and you can see and hear how the wave change. Let's see if it's this one here. System requirement. Okay, that's how you see. That's not what I want. I want to hear. I want to listen to that. That's sound waves, waves and sounds, physics simulation, understanding sound waves, visualizing standing wave simulation, exploring sound technology, sound simulation. Oh, some time ago, just so easy to find that. Light and sound simulation, interactive sound propaganda. Let's see. Let's see if I have any. No, I don't have any. Maybe my notes. Let's see. Speaker. Speakers simulation. Maybe simulation here. Simulation. Speaker simulation software. Sound simulation software. Beat speaker simulation audio. Sound simulation software. Let's see. Sound simulation. Reading simulation audio. Analysis sound simulation software. Let's see. How embarrassing. Let's see. I cannot find it here. Let's see if it's here. Bookmarks. Analytics. Patterns. Code control. First experiment. Sound harmonic. Let's try sound harmonics. Harmonics simulator. Maybe is this one here. The sine waveform has a single frequency building block of the maybe is this one. No. Let's see. Maybe it is. Yeah, it's one of those that we have there. Let's see if we can. Square waveform, sound waveform. Volume. Let's see. How do we play it? Okay, doesn't like. Okay. Here you go. Okay. So here you go. That's one of them. That's too loud. We have to. Okay, but that's not the one I want. But that's one of those. Okay, you can come up with sounds of different frequencies. Okay, here's the sound wave was 251.14 hertz. That's a sine wave. And then you have this other sound wave here that we don't want to mess up with. Okay, so what do I usually do? This one is not going to help us, but we're getting there. We're getting there. Waves and harmonics. Let's see. Use simulation to make some gravity. Standing wave in a pipe, fundamental frequency and harmonics. Each network. Let's see if this one works. Nope. Harmonics generator. Let's try generator. Sound harmonic generator. Ultra compact. I want waveform generator. No. Sound. Let's try the sound generator. Okay. Here you go. Finally. I got it. It must be this one here. Yeah. Okay. That's what I wanted. 440 hertz. See that I can have different type of sound. Here you go. I'm playing this one. That's not loud enough. You can stop. Okay. And then you can change the frequency. Remember the lowest frequency that you can hear is the 20 hertz. I don't hear anything. I do not know if you folks are hearing anything. Let's see. Yeah, I cannot hear anything. Okay, but what about 30 hertz? Yeah, I don't hear anything. I do not know if you hear. I'm gonna send you this online tone generator, okay? Online tone generator, so you can play with it. Doesn't have to be necessarily this one. Online tone generator, everybody. And I'm gonna put that in my notes as well. Yeah, I'm starting to hear something. Now, notes, not this one. This one here. Using an online tone generator, that would be we can explore this idea of beats. Okay, just this one here, just one of them. Notice that we can change only, by 1 hertz. Looks like I'm starting to hear something. Yeah, 100 hertz. Play. Okay, I'm starting to hear that. See that? We can have sound generators, frequencies all the way up to 2,000, 20,000, right? 1, 2, 3. Let's see. Oops, I cannot hear that. I don't hear that. Maybe I'm getting too old. What about 10,000? Yeah, I can hear that. 10,000 I can hear. 5,000. Whoa. Now it becomes more audible to me, okay? But it's not very comfortable for me. I'm gonna put 1,000 hertz. Okay. Okay. Lower the volume. I'm gonna put my no, it's not. I cannot hear it yet. Let's see. Close it. Uh-oh. Big problem. Got into big. Okay, now I can hear you. Okay, now let's see if I can live this way. What I want to do. What I want to do is to get 2 different frequencies and combine them, so you can experience exactly what beats feel like in real life. Okay, so what I'm going to do here, little trick. I'm going to open another page. Let me stop that for now. I'm going to open another page of the same. Yeah, I'm going of the same site. I'm going to put maximum here and maximum, so they can be at the same frequency. One is 440 hertz. I'm going to put this one 441 hertz. There's a difference in frequency of 1 hertz, okay, between those 2 sound waves. Here you go, 441 and 440 hertz. Do you see the variation, the beating? That's what happens when you combine 2 sound waves with a very small difference in frequency. And that's exactly what that equation is telling us. And that's exactly what this graph is telling us too. The peak is right here. and this peak has a period equal, related to the difference in the frequency. Those two frequencies are separated by 1 Hertz. F2 minus F1 is 1 Hertz. Consequently, the period of this difference is going to be 1 second. Okay. And now we can explore that even more. Both waves have the same amplitude, right? If I go back, if I make the frequency equal, let's see, 441, right? Yeah. See that? You feel no difference whatsoever, right? There is no difference whatsoever. But let's go back to 1 Hertz of difference. We gotta play it. Otherwise, we're not gonna be able to see that. I can go to 442 now. Play. Those peak in the amplitude are separated by 1 second. Okay. If I make the difference, 2 Hertz of difference, then you should see that the period is going to decrease. Okay. Do you see that? This is exactly what those equations are telling us. We have those vibrations that are very fast, 443 Hertz, that we cannot discern with the ear. By the way, it's going to be the 443 Hertz plus the other frequency, right? Even faster. And then you have the beating frequency that we can hear. And now I'm going to increase even more the difference between those two waves. See that? Right now, the difference between those two frequencies is 3 Hertz. And the time difference between those pulses that you hear is going to be 1/3. 1/3 of a second. Okay. Eventually it comes to a point that we cannot hear the beats. There you go. Comes to a point that we won't be able to hear the beats. Right now is 0.25. 39 is going to bring us to 0.2, right? 0.2 seconds. 5 Hertz, 0.2 seconds. We still can hear somewhat, but we're already reaching the limit of the human resolution, the human ear resolution. See, faster. And if I go to 430, right? 430 is going to be how many? 430 going to be 14 Hertz of difference. Okay, we can hardly hear the pulses, right? We can hardly hear the pulse, but let's put okay, now you can hear. That's going to be around 1/10 of a second. 1/10 of a second. Okay. There are some simulations out there. Let's stop. Otherwise, we're going to get crazy here, right? There are some simulations out there that they give you even a decimal place here. Okay, and then we can extend your beat frequency not to 1 second, but 2 seconds, 3, 4, 5, even 10 seconds. Okay, multiple tone generator. We have a multiple tone generator here. Every now and then they say multiple tone generator, everything RF, close. I don't want that. Okay. Penny, no, that's not what I want. That's not what I want. Sweep generator, peak shifter, time stretcher, voice generator, sweep generator, hearing test, noise generator, metronome, acoustic. Okay. Okay, so that's the idea of the beat, of the phenomenon of beat. We have a component that has a high frequency that we can hardly discern, and this component of low frequency that depending on the difference of the frequencies, you can hear that quite clearly. Okay, let's see if we can get another tone generator like that. Tone generator. Almost 2 o'clock, right? Tone generator designed to be simple. Sponsored online tone generator. Online tone, maybe this one. Okay, let's see if I can. What I want a tone generator that can go to the decimal in the hertz. Okay, let's see. Maybe this one allows me to do. Oh yeah, this one lets me do that. See that? I'm gonna send that to you all, folks. That was the one that I used some time ago. Another tone generator. Another tone generator, which has higher resolution. Okay. And to play a constant tone, to change the frequency, drag the slide and press to adjust the frequency by 1 hertz. Okay. Or press shift plus and shift minus and shift now shift to arrow, right? That arrow. To adjust the frequency by 0.01 hertz. That's what I want. Press to adjust the frequency by 0.01 hertz. Control plus. Okay, let's see if we can do that. So adjust 0.001 hertz. But what's the difference here? I don't understand the difference. Control, half, double the frequency. Change the wave type. Okay, let's see. Let's see. I can get. Here you go. Yeah, I can do that. Okay. Okay. The other one doesn't allow me to do that, right? Now I can play with a tenth of a hertz difference. But I have to have both of them playing together, right? 430, 429, okay. 430. The other one, 440. Let's go to 430 here. 430 and 430. They are both harmonics. They are waves. They're sine waves. Okay, and then I'm going to adjust the other one to 430.1, even better, 0.2. We are going to have a 0.2 hertz difference between those two frequencies, which should allow us to hear a beat of roughly 5 seconds. I think 5 seconds is too long, right? Let's go a little bit more. Let's see, 2 seconds. Half frequency, half hertz of a difference in the frequency, 430.5. Okay, so let's see. Play. Okay, just one playing. Let's get the other one playing. Just time it with your watch and see if you can really measure 2 seconds. You can count the beats, right? Count the beats and start timing, just like I'm gonna do here with my watch. And then confirm that you have a 2-second separation between those beats. And I'll try to lower down this. Oh no, oh no, I didn't do what I said. Okay, let's stop it. Okay, so let's do that again. I want to decrease the volume. Okay, that's the volume here. This one, 430, 430 as well. Okay, the other one is going to be 430.5. Where's the volume? The volume is here. And the volume is here. Okay. 0.5 hertz. Play it. 0.5 hertz. Play it. So I'm going to count down. 3, 2, 1, 0. Oh no. 2, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pulses. I got exactly 20 seconds. Okay, try it on your side as well. If you want to make it, the difference even greater, right? In period even greater, you can adjust it to 430.1 hertz, which is a tenth of a hertz, right? A tenth of a hertz would give you a period of the beating equal to 10 seconds. Okay, and that's what the beating phenomenon is all about. Look again. There are even nicer things that we can do with those generators. Here I'm combining only two tones, only two slightly different tones. Okay. But then you can start combining 3, 4, and 5, and then you're going to see something even more interesting. Let's do that. Yeah. I'm going to, third one. Let's go for a third one here. That's 430, 430.5. What I want to do. Let's see, leave this way. Let's see, 430. I'm going to put 431 in the other one. Let's see what we get. Yeah. One 430, the other one 431, the other 430 and 0.5. Okay, so I'm going to play them. Okay, the second tone generator. And then what about the third one? It's a different behavior. You can see there's a different behavior, right? And this one should be 50, I believe. Yeah, they are all turned 50. Good. It definitely is a different behavior, right? So let's go stop this one. You can see that the smoother rising in the sound compared to the other. This one is not as smoother. This one, you start to see like a more pronounced peak. And by the way, that's exactly what you're going to observe, that you're going to hear if we add more of those tone generators. Okay? Let's stop here and stop. It's 154 right now. Okay, and a better tone generator is this one. Yeah, this one here. Can adjust, it has a higher resolution, a better tone generator with a higher resolution is this one. Okay. And So I think we can stop here right now. Going back here to we have beats. I didn't cover Doppler effect yet. Okay, I'm not gonna cover everything that's in this chapter, but beats, and we'll cover Doppler effect. What I want to do, let's stop here for the exam, right? Otherwise it becomes too much stuff. Exam 1. For the exam 1, and then the next meeting, I will cover some material that won't be in the exam 1. 33.3, 17.6 is beats. So we have everything that we need here. 17.3 is interference, 17.5 source of musical sound, and 17.6 beats. Okay. It's going to be 4 chapters, but the exam is going to be next Thursday, 7 days from now. Okay. Let me show you the syllabus. Syllabus is right in here. It's going to be part, part of 7. Yeah, it's not good. Chapters 15, 16, part of 17, and 33. Okay. That's what the exam is going to be. Today we covered a little bit of 17 as well. And previously we also did cover a little bit of 17. A little bit of chapter 17. Let's see. Okay, now we have it. Chapters. Like that. Any more questions? So we can stop here right now and we meet again. Remember, it's going to be a holiday on Monday. We meet again on Tuesday. And I have office hours right now, if you want to hang around. Okay? So see you on Tuesday next week.
Have a good day, Professor.
Hi. See you.
Hi, Professor. So you said it was so it's 15, 16, partially of 17 and 33 will be the exam, correct?
That's right.
Okay. And then any material. Oh, go sorry.
Just check it here. Here you go. See, I have the sections, and then you can guide yourself by the notes as well. What you're gonna ask?
I was gonna literally say what you're saying what you showed me right now.
Okay.
Yeah, 33.2 and then 33.3.
Yeah, 33.1, 0.2, 17.35, and 6. Okay.
And everything we do next week is probably going to be for the next exam, if anything. I know we're going to do the labs, but
yeah,
it'll be for the following week, correct?
That's right. Everything that we do next week is going to be for exam 2. Okay.
Okay. And then lastly, I did have a concern at the very end of the semester, not on the final day, but the day before. I'm transferring to Cal State Dominguez Hills this fall, and my class registration day is on that Wednesday, not the day of the final, the day before the final.
Okay.
I just wanted to give you the heads up, and I'll send you an email for a reminder.
Okay.
But on that day, the day before the final, I won't be able to come because I will be it's a mandatory attendance. Yes.
Yeah. Okay. That's okay. You're just missing a lecture, right?
Yeah.
Maybe I'll change a lab here for you. Okay. Let's see how maybe I reschedule the lab, and you won't miss the lab. Okay. But just a lecture.
Okay.
But
Thank
you'll
you,
be
Professor.
able to make it for the final, right?
Yeah, my registration is on the 7/12, not the 13th. So
Okay, 7/12. Okay, that's good.
okay, thank you, Professor. Have a great weekend.
You too. Bye-bye.
Bye.